يا جماعه اشتغلوا الاجنده بس. اشتغلوا الاجنده بس.
تمام. صباح الخير يا جماعة. Good morning everyone. Sorry for the delay, but now we see that the hall is complete almost. So today we have a very exciting collection of sessions, and we are going to start with very wonderful session about quantum systems and information. Yesterday, we have seen the challenges of the hackathon, different talks about the education and the ecosystem. We have seen from our professors the diversity of researches in Egypt, but also in Africa in general. Today, we are going to start our session with Professor Ahmed Al-Mahdi. He is the Dean of the ITCS School at Nile University. He joined Nile University in February 2023. He got his master and his bachelor and the master from Alexandria University and PhD from Manchester University, UK. Coming from a computer systems background, Professor Al-Mahdi is now exploring making quantum computing usable in practice. His group is exploring quantum AI, dealing with quantum noise, developing self-healing quantum memories, and doing practical quantum communications. And he has very strong collaborations with different and many international universities. Welcome, Dr. Ahmed.
بسم الله الرحمن الرحيم. صباح الخير يا جماعة. اشتغل. طيب يعني أنا مجهز كده presentation. اوكي. طيب أنا يعني إيه I will try to be brief. طبعا I am so happy. Sorry, I have to talk in English. Yeah, all right. So I'm really so happy and honored to be with you here. And actually, yeah, so as Dr. Taha kindly presented me, so I'm actually more into systems guy. I'm coming from computing systems background, computer architecture, parallel computing systems, and so on. And of course, I am so fascinated about quantum computer because of like the acceleration, the speed, the potential. And again, I like to make things happen. So I am more into the, let's say, the how to make the systems work. So my focus today on the talk is about the error mitigation. And as you can see from the agenda or the outline, I'm just going to give you a brief introduction to quantum systems from the way I see it. It's not really high level. I like to go deep a little bit. And then I'm going to talk about error mitigation. And basically, this work has been done by our group, actually. And yes, I think already I've been introduced. So I'd like to introduce my team. So I'm really so proud to have all these people with me, so honored. I think Professor Salem Higazi might join today, I'm not sure yet. And as you can see, I have, actually many doctors and professors, which I'm really so happy about that, and many master students. And actually, I'm very lucky also to have collaboration from universities from Tokyo in Japan and the Gulf and many other places. And I think working alone, of course, is not the message here. It's really the teamwork. Yeah. So I'm also have undergraduate and so on. All right. So maybe I'd like to start with just basic concept in quantum computing because again, I am systems guy and I like to see the things from the low level a little bit. So let's start by a very simple question. What's a quantum, right? So does anyone know what's a quantum? Well, I say quantum computer, quantum mechanics. What is a quantum? So so maybe just to save time, it really goes back to Albert Einstein. And maybe I'd like to show you some live demo, hope it works. Some very interesting experiment that has been done in like maybe more than 100 years ago, very long time. So I don't know if you've seen this before. This is called the photoelectric effect. Have you seen this before? Okay, good. So anyway, so what they did in the past, they have this kind of very interesting experiment where you can change here the color. There is some light here, okay? And you have some material here, right? In this case, it's like sodium, whatever. And then you can increase the intensity of the light. So what happens here is that this light is like energy, right? And when you kind of turn on the light like that, this energy somehow excites the atom on the surface. And if the atom is excited and so on, electron can leave the surface and move. And then you have electricity. All right. So if I increase the intensity of the light, so this means that now we have more energy, right? But nothing happens. There is no electron that moves. Nothing happens. All right. So maybe the energy is not good enough. All right. However, if you change the color of the light, see what happens. Electrons start to flow. So this puzzled scientist. Why? This is for the same intensity setting, same power setting. Why changing the color makes, you see, going into like high frequency, things go crazy and electricity goes like very fast, right? So the question is, why? Do you know why? Sorry?
Like that means more energy to get
Yes, but if this is the case, right? So if I'm here, let's say, all right, and now I increase the energy, maybe I can put here infinity if you like put some light bulb like that with like megawatt. It's still not good enough. So this is much big energy, right? So no, it doesn't work. Yeah. Yes, but if this is the case again, I can make this my megawatt bulb, right? I can use the dam of Aswan to turn on one light bulb. So you can use the sun, for instance, yeah. So you can have much energy as you like, right? So this was really a big puzzle, but yeah, maybe one last. No, again, because the energy, just to keep it very simple, what Einstein said, let's go back to the presentation. Yeah, so Einstein just said, actually, light is just a form of discrete units of energy. It's like having packets of energy. One packet, two packet, three packet. So if you put like million packet, it's okay, but everyone has got fixed amount of energy. So you can think about it as these units of light or energy, they call it photons. So it's like a particle. It is a particle in a way, right? But this strange particle, it's got like fixed units of energy, 1, 2, 3, and so on. And this explains what happens. And actually, he got his Nobel Prize because of that, just to understand that it's quantized. The light is composed of photons, and these photons has got some energy. And this energy is actually depending on the frequency of the light. So energy equal H, which is the Planck's constant, and V is the frequency of the light. So when you increase the color, or the color when it becomes like magenta or so on, it's more energy. So it's like you have packets, and every packet has got high energy. Now this packet goes to the electron, and then the electron energizes and leave. So you can think again as like you have some ping pong balls and you throw it to some atom. So if you keep throwing with very high rate, it doesn't matter. What happens is every ball has got fixed amount of energy. So if this energy is not big enough to get the electron out, it will make nothing. Right? And this actually changes many things. And the word quanta means like units, 1 unit, right? Quanta. And of course, quanta and quantum. So quantum is the plural of quanta and so on. Quantum is one and quanta is plural. All right. Now, second thing. Now, this kind of strange world where you have these packets of energy or photons and so on. So how do they behave? They don't behave like the mechanical system at all. All right. So how do they behave? They actually different. So let's go back to the mechanics. What is mechanics? I think you all studied in school or university that this famous, like how to say, Newton laws of motion. You have a mass like that, like this is the apple, let's say, and this mass like goes down. And if you label this axis as x, and then you can work out according to the mechanics that there is some force pushing this down, and this force is proportional to the mass, right? And g is the gravity, acceleration due to gravity. But what happens at the end is that you compute the state of the apple, right? So the state of the apple here is like where it is at certain time. So at time 0, maybe it's somewhere. Now at time 1, where would that be? Right, so if you put here t0, according to this equation, it will be like 0. So we say this part is 0. So if I change t here to 1, whatever, so you start to move on, right? And your location is here. So this equation, you can derive it using the mechanics that we all studied in school, right? So this is classical mechanics. Now, what happened with the quantum mechanics? Things are so crazy, and I always like to go back, very much back in time, to 1804. That's a very long way ago, right? And at that time, there is a very famous, I think, British scientist called Thomas Young. And he did his very famous experiment called the double slit experiment. And this was very strange. So actually, he put some laser, or some, not laser, at that time was the sun. So he made the box, and they got the light from the sun. There's 2 slits on the box, and in the back of the box, he gets some pattern like that. So yeah, so this was strange. Why? Why it's kind of dashed pattern? What happens? All right, this was very strange phenomenon. Why? What happens? So anyway, so yeah, maybe because of time now, but anyway, I can give you the link. You can play with that. So somehow you can explain this pattern as if the light behaved like a wave. All right, maybe quickly I show it to you, and maybe I'll skip at the end because this might be interesting. All right, so actually all the animation I'm showing you, actually they are developed by a scientist, and actually I can't remember the name of the guy now, it's in the slides, but he's also a Nobel laureate. All right, so yeah, so anyway, so yeah, as you can see here, if I just play, you can see that there is a wave here. There's like water, and there's like wave front moving, and the 2 slits are here, and somehow they are interfacing, interfering, sorry, together like that, you see, and they're making this kind of interesting patterns that somehow exactly looks like the pattern that he got in this 200 years experiment. So this puzzled scientist, and they start to think like, is light a wave? Is it particle? Is what? This was a long time ago. But when Einstein came and said just light is just photons, this was very interesting. So how can you explain this interference pattern? All right, so okay, now comes Schrödinger. Schrödinger was asked a question like that in maybe yeah, it's about more than 100 years ago. And I think, yeah, it's exactly 100 years. And that's why this year is the year of quantum, as you all know. Right. So actually, he's been, yeah, asked like if then somehow the particle will behave as a wave, then there should be some wave dynamics there. There's some wave equation. How can this wave behave? How can it be generated? What happens after t? So like when we talked about the quantum mechanics, we said, give me the position of the apple at time t. So now give me the wave at time t. So how to do that? So he came with a very famous equation that actually is in stone, which is the Schrödinger equation. And it's long story, of course, but you can see that this symbol represents the wave, and this symbol represents the energy somehow. So somehow the system or the wave evolves, yeah, depending on the amount of energy you have. I know this is a bit complicated, but just to make it simple, I'll show you another demo now. But before showing you this demo, the essence here of wave is very strange. It tells you like, all right, so don't worry about where is the photon or why the interference happened or everything. Just think about the photon as a wave, all right? And this wave somehow explains the state of the system. And when you look, it disappears. Yeah. So anyway, maybe I talked a lot here, but let me show you a demo just to understand what I'm saying. If you look at this nice animation here, all right, okay. So what's that? Let's pause here. Okay. So we have here, this is a source that releases some photon, you can see here. And then at a certain time, maybe I can start from the beginning, it will be easier. Let's reset. Okay. And actually, let's put the two slits again, and let's, yeah, make them close slightly like that. And let's start by just one step at a time, like that. Now, what happens here? As you can see, this kind of magenta thing looks like a wave, right? There is something moving here. Now, every pixel here have got a color. This color is we call the amplitude of the wave. All right. Now, yeah, just to keep it maybe, sorry for that, but maybe it's a little bit complex. This number here, it's not a real number. It's a complex number. So that's why they call it actually a complex amplitude. Now, this is very strange. Yeah, nobody understands why it's complex, but it works. All right. So you can think about the wave as something like that, but these points are actually two-dimensional. There is a color and there is other color maybe or whatever representation you like, which is the phase or whatever. Now, what it tells you here is that this is the state. It's not like I'm telling you the apple is here at that time. I'm telling you at this moment of time, this is the wave. So where is the particle? Do you know? Where is the particle? Where is the photon? So Max Born told you that if you take the amplitude of every point here and square it, you get a number. This number is actually the probability that it will be here. So this basically gives you a probability distribution of where to find the particle. So if you don't look, it will be like that. If you look, it will be only one pixel here, depending on the probability and your luck, and everything else will be black. Now, to explain what happened in the two-state experiment, you can see this is what happened here. So at this moment of time, it says that there is a chance to find the photon here, to find the photon here, to find here, to find here, to find here. But as you can see now, it's like saying the photon or the wave is here and there, right? There is a wave here and here. So if you don't look, there is a wave here, amplitude here, amplitude there. So it's like saying a photon is actually here and there and there and there and there and there, all this position at the same time. And I think this kind of strange phenomena, I think they call it superposition, which means that it's no longer this apple is in there, right? Actually, it's kind of all these places, but when you look, it will be only on one of them, right? So this is very strange, but this is how it works. Nobody understands why up to this moment. And there are many interpretations, like there is a Copenhagen interpretation, there is, I can't remember the others, but the Copenhagen is the most famous one, and this is what I just explained to you. Now, back to our example. Actually, I generated this pattern using YouTube video. If you get some hair like that, and you have a laser, and put it like that there, and look at the wall, you will find this pattern. So where is the Wave equation here? So you can say like that, if this spot is red, the laser is here, right? So this means that I made an observation and the laser hit this space. When it's dark, this means that there is no photon here whatsoever. And when you turn the laser on, you have like billions and billions of photons flowing, right? So as if you're doing many, many observations. So you can tell there is nothing here, that the wave here is zero. The wave here is very high. Here is zero, and so on. And actually, we made this video. I'm sure if it works, but well, yeah, I can give you the code as well. You can try it yourself. We just use some equation here. This is the wave function. And actually, maybe I can just go back. Yeah. So you can see here, now I have some particle. This is after like the slit, the division from the slit. And you can see when these two waves gets near each other, they start to interfere like that, you see. And actually, what we did here in this very simple code, we just run the solution for Schrodinger equation, which actually explains the state. So as you can see, every moment of time, the wave like moves and interfaces with itself and makes this very nice interference pattern. Okay. Of course, you know the Schrodinger cat. I'm not going to repeat that, and so on. So let's move on. So now, in order, so this is like basic phenomena. And then, of course, when you look at the quantum mechanics, they tell you the state is the wave function. And the wave function is basically what I've shown you, the wave. But if we're working now with digital computers and so on, we like to have a notion of a qubit, right? A discrete state. It's not like everywhere. So maybe we can use again the two-state experiment to explain that. Maybe I would say that if the photon is up, this is location 0, so this is state 0. And if the photon is here, this is location 1. And now we mentioned that there's a complex number here. Maybe we can represent this complex number as just very simple wave with the amplitude and the phase like that. And then you can say that the state at this moment is basically these two complex numbers, the complex amplitude here and there. And usually in quantum mechanics, this is what we do. We say now we have two numbers, so a nice way to represent these two numbers is just using a vector, right? And then you have the Dirac notation, so so you can represent it like that. This is normal vector, and then 1, 0 is like that. So you have some linear algebra to represent your state. So a vector becomes your state. Right, and of course the interference can be explained by just adding these two numbers, and everything works. And if you work out the equation, this is what I did, you actually can see this is the interference pattern, like this is the x-axis here, and the y-axis is like the probability of finding the photon. So you can see it's very similar to what you get from the experiment. All right, so now if you build the quantum computer, we start with a qubit, as I mentioned. And of course, you've seen the block sphere. I'm sure you've seen it many times. But what's interesting here is that the state for one single qubit is basically any point on this three-dimension sphere. And this is crazy, because this means that a single qubit can represent, like, in theory, infinite values. And this is where the quantum information kicks in. Right, of course, you know about the quantum mechanics. I don't need to get into that now, but it's just, because of the time. And I just want to quickly, just before going into the error mitigation and so on, to show you, like, actually, this is like some simple experiment I made just to understand how quantum computer works. And basically here, I tried to say, like, I want to detect the case if it's like a game. It's a very well-known algorithm called Deutsch or whatever, but I just implemented it using very simple light interference. So I just like engineered a very simple system with 4 slits like that. And somehow if I have 0 and 0 here, I made the interference to be like constructive. And somehow if you look here, you will find some light. Yeah, anyway. And if you have like two different numbers, you get 0. You don't see light. So the whole puzzle here is like, I'll just give you some numbers. And if they are the same, you tell me they are the same. If like half of them are 0 and half of them was 1, you tell me that. So to do this quickly, you can just use a very simple interference like that, or you can do it even with 3D and shed the light like that and get the interference. Anyway, I'm just trying to show you that you can build many things with this crazy interference idea. Now, maybe I just to quickly just to give you some impression of this, the complexity here or the power of quantum computer. I know maybe you've seen this before, but just quickly, if you just have one qubit and you are just allowed to be on 0 or 1 or both, right? So you have like 3 possible combination, right? Now, if you have 2 qubits, what are the possibilities? If you just have like zeros and ones, like superposition between these chains. So you can say that I have 0, 0, right? I have 0, 1, I have 1, 0, I have 1, 1. Anything else? No? No, it can be 0, 0 and 0, 1. Anything else? All right. If you like math, you can work it out. If you have n qubits, you can actually represent 2 to the power of 2 to the power of n different states. And this, if you just use maybe 7 qubits, you can have a number which is larger than the number of atoms in the universe. Only with 7 qubits. All right, anyway, now we move on from this kind of simple low-level representation into, again, to the quantum mechanics or quantum computing model. Of course, you've seen the circuit model, and basically you have some gates, and these gates, of course, operate. So you have states here, like you trace the circuits, you start here with some input state, you do some operation like Hadamard, you get some new state, you have C naught, you have another state, then you measure and you collapse and so on. Right. So this is the circuit model, and it's very famous. And of course, you know the gates. I'm not going to take time on that. And now we are getting more into quantum systems. So let's look about how quantum processor looks like. Usually, what you see here is typical quantum processor based on the superconductive technology. What you see here is basically like a fridge. So it's cooling. So the processor is somewhere here inside this shield. And all of that is like cooling. So, but let's go inside the quantum processor. What's in there? So actually, conceptually, it's so simple, right? You have some, of course, you have some classical processor, which is usually called like, maybe host or whatever. And then you have your quantum processing unit, which includes some control processor and the actual quantum hardware. So the actual quantum hardware, you have the qubits, which everyone can be 0, 1 or crazy 0 and 1 and so on. And these links actually tells you that you can do like 2 qubit operation like C naught. So you can do C naught between this and this, but not those. And the whole idea is that every cycle you execute some gates. You say, this is Hadamard, this 2 C naught, this one maybe not, and so on. And then you can read if you like or not. So it turns out to be like, it's kind of sequence, like standard, like in the classical world, like you have some fetch, execute, it's like that. But here it's like execute, read out, execute, read out, execute, read out. So it's kind of sequential execution. Right, so this is how it looks like. Of course, there are many technologies, not just superconductors, there are trapped ion, there are photonics, and we are actually at Nile University very much interested in photonics because we do believe that it's much cheaper to implement, and usually you don't require the cooling that is so expensive. But for us as computing engineers or scientists or people interested in building computers, of course, you also should be interested on the stack, like the system stack. Like in classical, we have transistors, assembly, high-level language, and so on. In quantum computer, you have different things. We have, of course, very low-level language, and we have lots of things here in how to compile, how to do error correction, how to mitigate noise, optimize, and so on. So most of the work nowadays actually happens here for the software guys, how to make the computing reliable. Because up to this moment, of course, there is lots of hype, and of course, we all like quantum computing, but usually people are still skeptical, right? So can it really do something? Of course it can, or we believe that, but up to this moment, we still don't have a very concrete things. We have maybe some toy examples and so on with some interesting problems. Yeah, so it's all about the noise. If we can decrease the noise, if we can scale up the number of qubits, if we can build what's called the fault-tolerant quantum computer, that's what we're looking for now. So the current era of computing system, usually it's called the NISQ, according to John Prescott from Caltech, which is the noisy intermediate scale quantum computer. But now we're saying that we are entering the LISC, the logically intermediate scale quantum computer. So it's like logically fault tolerant, but the number of qubits is not very high. So now I think IBM is the leader now with like 1,000-ish qubit, and they plan to increase more. But recently, a few months ago, there was like new technology from Microsoft called Majorana, or I haven't really studied it yet, but it's sophisticated, and they claim they can reach millions of qubits, but we're still waiting to see what's going to happen. So now this was like a quick introduction to quantum systems. I'm really sorry for taking most of the time, but now I'm just maybe give you some highlights about our research here in error mitigation. All right, so basically I'm going to highlight two things, right? So of course, the quantum system now are noisy. So this means that if you have some state, of course, it can change and it will not last for a long time. It's so fragile, right? So basically we did two things. The first is to characterize the noise, to find out how much noise is there. And usually this is called the state fidelity. All right, so let's tell you like more information about that. And if you're interested, you can find the paper here. It's open access actually, and thanks to the Egyptian STDF, the Egyptian Knowledge Bank, it's actually, they paid for that to make it free accessible, so you can access that. And yeah, so basically just to keep it simple, in order to tell how much noise you have in your circuit, yeah, it's so difficult process actually. You have to start with some circuit and do something called the tomographic measurement. All right. Have you heard about tomography before? No. Okay. So you can say that this is very expensive way to find, yeah, to characterize the error. So basically if you have 1 qubit, you have to repeat or make 3 experiments. If you have 2 qubit, it's 3 to the power of 2, it's 9. It's exponential on the number of qubits. So you have to do exponential number of experiments. And from those experiments and measurements, you reconstruct the quantum state. And I think the world leader here is, I think it's called Jay Gambala from IBM. I think he's the guy who made this very efficient, or this step very efficient. And then you got the fidelity. Right? So what we do in our research in our group was that this was actually back at that time in Egypt, Japan University of Science and Technology. So we proposed a very different approach using just classical machine learning, where we tried to train some network just to encode the circuit and give it to this network and try to predict the fidelity without doing this 3 to the power of n experiment. So this was very ambitious goal. And at that time, actually, the number of qubits was like 5 qubits. This was like 4 or 5 years ago, or slightly, maybe 3 years ago. Yeah. And actually, as you can see here, we started experimenting with like thousands of circuits. Yeah. At that time, actually, the quantum processor access was for free at that time for this 5 qubit. So we made use of that. Took us like maybe 1 or 2 months full time on a quantum processor. But in today's, yeah, it'd be so expensive to do. But at that time, it was so cheap. It was free, actually. So what we did here is that we got a circuit and we made some encoding. So as you can see, like this is C0. So it becomes here, yeah, that's 5 from 5. This is C0. This is RZ, rotate Z gate. This is another gate, the same, and then square root X. So we encode basically these circuits, these numbers. And then in the quantum processor, we have this called the topology. This is the hardware. So you like this is qubit 0, qubit 1, qubit 2. And this edge means that you can do actually CNOT or, yeah, 2 qubit gate on these two. So we model this here, right? So every link here we mentioned 7 is like nothing, 8 is like CNOT, and 6 like CNOT, but the other way around. So here, like for instance, between 0 and 1, we have a CNOT. So that's why we have the 8 here. Now between 1 and 2, we have CNOT, but it's the other way, 1 and 2. So it's here, the second stage is 6. So anyway, so we encode this circuit with some matrix. And of course, it can be a vector. Let's flatten it out. And we started to make some machine learning model here. It's long details. I don't want to get into that, but just a standard convolution neural network. And what's interesting at the end is that we managed to estimate with really not bad accuracy the, this is the predicted fidelity and this is the ground truth value. Of course, you can see there is some noise here. Ideally, it should be, along this line. And what's interesting, actually, we found some interesting noise in the quantum system. So you can see like we're running some random systems here. The y-axis is the fidelity, or like how good you are. 1 is perfect, of course, 0 is so bad. And we just randomly generate circuits. And you can see during this time, something odd happened. And there were much noise there. I think it's called maybe dynamic. I can't remember the name now, but this phenomena has been reported elsewhere. And what we did, we just did some pre-processing and we tried to remove these kind of episodes where the noise was excessive. And interestingly, this is what we got. So this is before and after. So you can see now our prediction becomes much accurate actually before, after removing the noise. Anyway, so we tried that on 1, 3, and 5 qubits, and we showed that somehow the system really works. And actually, we run on some quantum benchmarks. This is a set of known circuits. And what's interesting is that, this is the ground truth fidelity. This is what we got. It's really nice. And our correlation was 0.967 or 8, sorry, which is very nice. And this is what you get if you just use some simple heuristic. So I think it was really not bad. Now, the next thing we did was now we can somehow estimate the noise. So how to decrease that? And this is what's called the error mitigation, right? So so we actually, of course, this is a very big problem, but we focused only on very important sub-problem here, which is the CNOTs, right? Now, if you look at this circuit, for instance, if you have a circuit like that, like a simple, like 3-stage circuit like that, and you want to operate here the CNOT between qubit 0 and qubit 2. Now, if in your hardware and your quantum processor, you don't have like an edge or, so it's not possible to directly, it's like that. This is the back end here. So you can operate between 0 and 1 and 1 and 2, but I want 0 and 2. It's not possible. So what should we do? We have to swap. So we have to swap qubit 0 with 1. And this swap can actually be implemented by 3 CNOT operations. So in order to implement this simple 3-stage circuit, now it became more deeper. Actually, it was 2 here. So now it became 5, depth 5. And the more you increase the number of gates and the depth of the circuit, the more noise you have. All right. So one simple idea was like, so why should I map 0 to physical qubit 0? If I just do simple mapping and change the order here, something like that. It should be very simple, right? So if I map just Q1 to 0, Q0 to 1, and 2 to 2, so it's just basically like swapping these two together, then you can do it directly, right? So now this is the problem. So as you can see, the choice of the initial mapping between the logical circuit and the physical is so important. So we ask this question, would it be possible to find out an initial mapping to decrease this number of CNOTs? And actually, maybe here you have only one CNOT, but you can imagine if you have a very big circuit with many CNOTs, it becomes more difficult. And usually this problem, they call it routing problem, because it's like you'd like to connect 0 and 1. It's like moving some packet or so. It can, yeah, there is some similarity between this one and the routing problem in networking. All right, so what we did, we actually used, again, classical or non-quantum machine learning. We used reinforcement learning to do that. There are lots of related work here, but basically they were not very general and basically used based on heuristics. So yeah, so we actually proposed a simple system based on reinforcement learning. Because a very simple way to do it, of course, is to try all possible combination, which is factorial n. But we used machine learning with reinforcement learning. I don't know if you've heard about reinforcement learning. It's so famous, using agent. And we formulated the problem as a learning problem with reinforcement learning. And we actually did that on 84,000 circuit. This is a lot. Yeah, it took a lot of time. And we, again, I don't want to take much time from you, but we started to only focus on the CNOTs, and we find a way to encode them and represent them in a matrix way. And we just use a standard reinforcement learning models called the active critic neural network model and train it on this data. And actually, interestingly, we managed to get very interesting results. These are standard set of benchmarks. And the column at the end is the improvement we got. So this is the number of logical CNOTs. And these are the new CNOTs we had to add for the swap using the state-of-the-art methods. And this is our approach. So yeah, most of the time we are actually better. And I think any improvement you make is significant. And also, yeah, you can see here our representation here is actually simple. And yeah, for other systems here, the representation is somehow dependent on the number of CNOTs, but ours is constant. And actually, our approach was much faster and scalable. Yeah. And I'm very proud that actually this work was cited by IBM, Quantum actually, and we're very proud of that. And yeah, we have very interesting citations now. So anyway, so I'm really sorry to take maybe more than the time allocated to me, but I just wanted to give you a hint about what's happening in the quantum, error mitigation quickly, and give you some background about how kind of quantum computer works in a very simple way, I hope. And the take-home message here is that now, I think what we are moving for is this LISC, logical. Now we are like intermediate scale. The number of logical qubits that are fault tolerant are very few. And I think now the future is basically about this fault tolerant, and we want to make a good computer that it does not suffer from noise at all. And I think this is really a strong goal. And and I encourage, of course, people to consider working in this area. Thank you. Any questions? Sorry.
Any questions? Yeah, so I have a question myself. So how do you see the future of error mitigation and how far we can reach? So with this, what would be the end game of error mitigation? Like now that we have the gross code from IBM, while we had the surface code before, and of course, with every type of code there is progress. But what would be the ultimate progress with the techniques or the extrapolation one?
Okay, so this is a good question. The answer is I don't know, of course.
But your opinion.
But to be honest, I think we shouldn't really only think about this frame of reference of mind where we consider the traditional error correcting code. Maybe there's something else. I know now we are working on people considering the variational quantum circuit, and variational quantum circuit somehow works, right? So maybe instead of just dealing with the error, maybe we can live with it and try to find something. I think this is kind of doable. Yeah, but the other goal, of course, would be great. But to be honest, I don't know. Thank you.
Thanks very much. I think that I think the idea of live with the error and try to scale, maybe that will might be the potential.
Yes.
Thanks very much.
Thank you.
Today. Thank you.
It's my pleasure. Thank you.
And now, we move to Dr. Salim Higazi, speaker. And Dr. Salim is going to talk about quantum processing and photonic degrees of freedom. Yeah, so I'm sitting down.
It's another presentation.
This one you sent in the another one. Oh, but maybe the so yeah, the talk will be about building secure quantum communication systems. Dr. Salim Hagazi, as an associate professor in Cairo University and also Nile University, he received the bachelor degree with honors and also his diploma and master degrees in electronics and communication engineering from Cairo University in 2002, 2006, and 2011, respectively. And his PhD degree in quantum optics and quantum information in 2017 under a joint supervision scheme between NILES, the National Institute of Laser Enhanced Sciences, Cairo University, and CREOL, CREOL, the College of Optics and Photonics, University of Central Florida. He served as the head of the Laser Engineering Department at the National Institute of Laser Enhanced Sciences at Cairo University from 2022 to 2025. And also he was a research associate and the founding director of the Quantum Communication and Cryptography Lab, UCCL, at the Wells City of Sciences and Technology since 2025. He has been associate professor with information technology and the computer sciences school at Nile University. His research spans optical processing of quantum information, photonic quantum computing, practical security of quantum cryptography, quantum random number generation, quantum photonic simulator, photonic entanglement, and optical communication, optical chaos-based systems, and optical image encryption. Yeah. عبد الرحمن عبد الرحمن لا عبد الرحمن البوينتر بس بوينتر ماشي البوينتر بس كليكر يا اليكس اه لا خلاص هو كده كويس هو ده نفسه الدكتور سالم
السلام عليكم. بسم الله الرحمن الرحيم. It's my honor and a pleasure to be invited to this event. My talk today is about building secure quantum communication systems. So all of us know about the secrecy of quantum cryptography, but today we'll reach a further distance by talking about implementations and the quantum systems. Whenever there is implementation, we will have non-idealities and non-imperfection, and this will affect the security. This is a campus of Nile University at Cisco. So let's start by talking about photons. Why photons are our communication particles, our flying qubits? Photons are different. They are chargeless, massless, weakly interacting with each other. So they have long decoherence time, can be easily guided through atmosphere and optical fiber channels, can be delayed and manipulated using very simple optical devices existing in every lab, maybe in Egypt or any country. So quantum photonic systems, not only the quantum cryptography, but quantum photonic systems in general, can be implemented, can be readily implementable in Egypt. So let's move to one of the most important, and all of us know about it, one of the most important quantum protocols in quantum cryptography. I'll talk about BB84. Most of us knows about BB84, so we will start by talking about BB84. Then after that, we will talk that this is an ideal version of BB84. What about non-ideality of devices and how this non-ideality can be used to overcome the unconditional security we talk about. Okay, in BB84, we have Alice and Bob. Initially, in the first step, Alice prepares a random sequence of zeros and ones. Random sequence. So we need for random number generation. Okay, random number generation. Random number generation can be easily generated using a MATLAB, using C++ or any other language, but this is pseudo random number generation. And the attacker, okay, and the attacker will know very well about, maybe about deterministically about the sequence of zeros and ones that you have generated. So we will need for some physical process to generate the sequence, the random sequence randomly. There is a setup, and all over the presentation, we will talk about setups, how to implement this in your lab, okay? In this setup, we have single photon pulse, 50-50 beam splitter that split the photon wave function between two paths, and we have two single photon detectors, so there will be 50% probability that the first detector will be triggered, and 50% that the second detector will be triggered. If the first detector is triggered, so the PC will register 0. If the second is triggered, so the PC will register 1. So among a number of photons, we will have a very random sequence between zeros and ones. Nobody knows about which path the photon will be detected at. We are sure that the photon will be detected in only one path of them, okay? Maybe not detected at all because if we have a quantum efficiency for the detectors. But if it is detected by one of them, it will not be detected by the other, okay? So this is a physical random number generation. Nobody knows about the sequence in advance, and this is very important in security. So the first step, after the first step, Alice will use this random sequence to encode photons in some degree of freedom. Here we will have the simplest degree of freedom, the polarization of the photon. Polarization is the plane where the photon have electric field oscillations. It can be linear polarized, it can be circular polarized, it can be elliptical polarized, linear and vertical or horizontal or diagonal or anti-diagonal. Okay, so Alice will encode the photon in polarization degree of freedom by zeros and ones. But not like the classical encoding. Here in quantum encoding, we will encode the photons into randomly, mutually unbiased basis. What's mutually unbiased basis? Here we have 0 and 1, plus or minus. We have two directions of polarizations, horizontal, vertical, and anti-diagonal and diagonal. Whenever any observer, Bob, or anybody detects the photon in one of the on one of these, they measure the one of in one of these bases. This will not certainly means that Alice sent them, because it means, what about your basis? And if your basis is matched to Alice basis, there should be matching between your basis as a receiver and Alice as a sender. So we'll have encoding in 0 1 basis and plus minus basis. Here we have a setup, as you see. Pulsed laser generates pulses attenuated to single photon and then controlled and rotated the polarization using the random number sequence we have just generated on our PC. So sending this encoded polarization, encoded photons to Bob through the quantum channel. Okay, Bob on his side will measure photons. He cannot measure photons in horizontal vertical basis only, or plus minus basis only. Alice randomly switching between the two bases. So Bob on his side will measure randomly in the two bases. This can be actively made by using polarization rotator, another polarization rotator on Bob's side. Another setup which is more secure and simpler actually is using passive switching between the two bases. Here we have a polarizing beam splitter. We have polarizing beam splitters, this one and this one. The first one is measuring in plus minus basis. The second one is measuring in horizontal vertical basis. Plus minus basis space is made by this polarization rotator. Whenever a photon comes to this beam splitter, it can be equally likely to detect it along this path or along this path. If it is measured here, this means that it will be measured in plus minus basis. If it was measured on the other side, it will be measured in horizontal vertical basis. Nobody knows. Bob, Alice, anybody knows which arm the photon will be detected at. This is the security here, and this is important because it is natural without any switching. So in the fourth step, Alice and Bob will check the compatibility. They both used randomly two bases. So Alice, through the channel, called Bob and tell him, hello, Bob, tell me about times and the basis of your measurement. Bob, Alice, how are you? I'll send you the times that I measured the photons and at which basis I measured them. After that, Alice check the basis of Bob measurements and find the matching between the basis of Bob basis and her basis and tell him to drop some cases where the both basis was not matched something like here, for example, she sent her photon as horizontal in horizontal vertical basis, but Bob measured in diagonal anti-diagonal basis. So this will be dropped. Okay, all these events will be dropped with unmatched basis, and ask him to check some results of, so for example, the fourth event, fifth event, and sixth event. If both are matched, Alice will tell him to, okay, we have a secure quantum key, and we'll have a security channel between Alice and Bob to be used after that. What Eve can do? Eve needs to share the key initially. So first thing that anybody can think about, Eve can use cloning, for example. She may take the photon and make a clone of this photon and measure it without affecting anything. But this is prohibited by quantum mechanics. There's no cloning theorem. Very rigid and very rigorous and very simple to be proved by any first class quantum mechanics persons, that quantum particle state cannot be coupled perfectly. So the other thing that she can try to intercept the photon and measure it and resend another photon with her measurement. But if Eve has the same basis of Alice and Bob, there will not be a problem. Forever, Eve, the eavesdropper, the attacker, will measure the same measurements of Alice and send to Bob. No problem and no errors in this case. But because Alice basis and the Bob basis was not announced initially, at some cases, 50%, Alice will introduce errors. In 50% of the cases, 50% of 50%, this will be 25% errors. The main conclusion here is that the secret key, if shared with another party, Alice and Bob will notice a high error rate. And the other main thing that we know about quantum encryption and BB84, that quantum key distribution is unconditionally secure. The unconditional security principle means that your secrecy now is not based on the power of the intruder. If he is very powerful and have every knowledge and have very good experience, very good devices, can replace the channel, it will be ideal in this case. But these four ideal devices, for practical devices with imperfection, the security cannot be guaranteed. So let's check out some practical issues that we may face in quantum key distribution system. We will study two famous examples. One of them on the source side, okay, Alice, and the other one at Bob on the detection side. We will introduce imperfection, practical imperfection existing in our devices, and show how this will affect the secrecy of our key distribution. How to generate single photons? The famous method is using pulsed laser and attenuating these pulses, generating a faint pulses, which is very attenuated to a scale that we have few photons or one photon per pulse. This is ideal if you think that we can attenuate any pulse to reach the single photon limit. This is not accurate because we have a statistics, it's coherent states. And this coherent state is ruled by Poisson statistics. Nobody knows about the number of photons per pulse. You attenuated it, okay, you just affect the average number, the mean number of photons per pulse, which is written here as lambda. The energy of pulse divided by the energy of a single photon. Lambda is the mean number of photons, and using this attenuator, you just affected this parameter, which is the average number of photons. Okay, what about Poisson statistics? In Poisson statistics, the probability that we have number of photons n, if the mean is lambda, is ruled by this relation, P of n equal e power minus lambda multiplied by lambda power n over n factorial. Also, statistics, for example, can be shown here in this figure. If we have lambda equal 1, for example, so you try to attenuate the pulse to the level that you have just one photon on average in your pulse, you will find that there will be a probability about 0.37 that you will have no photons. It will be empty pulse. Another probability identical to the first one that you will have first one single photon, about 18% that you will have 2 photons, 3 photons, 4 photons, and so on. What is the problem in this case? The problem in this case that Eve can split the pulse, can split the number of photons and share photons with Bob without any notice. Let's check this example. If we take lambda by 0.1 here, the probability of empty pulse will be 90%, the probability of single photon pulse will be 9%, and the probability of more than one photon will be 1%. The problem here with this probability, the 1%, I mentioned this example because this example is used in the practical quantum key distribution system to limit the number of photons per pulse. Single photon source, not true single photon source. It's statistics, there is statistics, and there may be huge number or multiple photons per pulse that can be used for attacking. Okay, based on this loophole, this vulnerability, we will have one of the first practical attacks that affects the BB84 protocol. It's photon number splitting attack. It's called the BNS attack. BNS attack, photon number splitting attack. In this case, Alice and Bob have a practical lossy channel with 90% loss, for example. Alice send photon along the channel to Bob. This photon can be detected by Bob, but with some probability, this photon can be absorbed by channel. Here we have a probability 90% that this photon will not be detected by Bob. What Eve can do? Eve, in photon number splitting attack, typically have capabilities. She can replace the channel between Alice and Bob by a low loss channel and benefit from the difference of the loss. Eve can use quantum non-domination measurement to detect the number of photons here and then block single photon signals because she cannot share the single photon pulses. But if we have 2 photons per pulse, for example, or multiple photons, in this case, Eve can share based on the quantum non-domination measurement detecting that we have number of photons. She can share the photons with Bob, in this case, without any notice. The conclusion here that away from rigorous proofs of unconditional security of a lossy channel, the key can be shared by eavesdropper without notice. This is a huge problem. We talk about a paper in 1995 after BB84 by about 11 years, and by publishing this paper, the community was shocked. This is a problem, big problem, because we thought that quantum mechanics offer ultimate security, unconditional security. There is some system for Eve to attack this security without notice. From 1995 to 2003, for something like 8 years, this problem was shocking the community, and many scientists introduced proposals to overcome this vulnerability. The one which was the simplest protocol and the most effective protocol, that this protocol, when published in Physical Review Letters in 2003, this protocol actually deleted anything related to the photon number splitting attack, is the decoy state protocol. In decoy state protocol, Alice have a source that generate single photon pulse. This is okay. But in some cases, and intentionally, Alice will increase the number of photons average per pulse above 0.1, for example. Instead of 0.1 photon per second, we will have something like an average 2 photons per second, for example. And after that, Alice and Bob will measure the loss percentage in the first case of single photon pulses and in the second case of multiple photon pulses. If Eve was not launching the photon number splitting attack, X percentage and Y percentage will be the same. This is passive channel, and X percentage and Y percentage should be the same. If we have Y percentage higher than, or for the loss lower than X percentage, so we will have photon number splitting attack and the protocol will be aborted. The co-state protocol, very simple protocol so far until now, will used within the practical quantum key distribution systems. Okay, this is the first loophole on the source side. Let's move to the second loophole on the detection side. I'll skip about the physics in the single photon detector and how the single photon avalanche photon detect the photons, but let's just know about this diagram here. We have single photon pulses, okay, and this is a single photon source with 2 channels or 2 ports. The optical port that detect from it's interact with single photons, and we have electrical port to generate TTL pulses, electrical pulses, something like voltage up to 5 volts and with width something like 20 nanosecond. Ideally, the single photon detector just detects single photon pulses with some efficiency. But in another attack called detector control attack, Eve can illuminate the detector, the single photon detector, by blinding light. Blinding light will change the operation of the single photon detector from the Geiger mode to the linear mode. In this case, the single photon detector will not be sensitive to single photon. Eve will measure the single photons come from Alice and then generate bright pulses like this to trigger the detector on Bob's side. If the bright pulse is above some threshold, it will be counted. If under some threshold, it will not be counted. How this can be used to remote control the detectors of Bob? If Eve adjusted the level of the trigger pulse to be just above the threshold, in this case, if Eve has the same basis of Bob basis, the whole pulse will be go to single detector. It is above the threshold and going to single detector, there will be a clack. What if Bob have another or have the other basis? In this case, for example, Eve sending on horizontal vertical basis and Bob measuring on diagonal and diagonal basis. In this case, the energy will be split between the 2 detectors. Okay, by splitting this huge pulse, this smaller pulse will be less than the threshold. And in this case, no clicks will happen because we are under threshold. So this can be used to remote controlling the detectors at Bob's side without notice. It's different from the photon number splitting attack. Photon number splitting attack, as we said, was killed in 2003 by launching the decoy state protocol. But so far, we have a vulnerability in the detector control attack. Okay. For this attack, we have introduced a practical way to overcome detector control attack. This system, as you see here, we have On the gateway, we have a randomizer, polarization and randomizer, and a state converter. The state converter operating in the optical domain, it converts between path and polarization and time bend. Translate the polarization to time bend in one direction and translate back the time bend to polarization in the other direction. The same thing for the path. So let's review the steps of this quantum key distribution system process. Initially, we have an initial state of psi1. Psi1, here as we wrote it, in polarization and the path. So we have a photon in diagonal polarization in path A. So we are in path A here, and this laser inject a photon of diagonal polarization through the polarizing beam splitter. The horizontal polarization will go through the longer arm, and the vertical polarization will reflect on the shorter arm. So H will turn to T long, and V will be translated to T short. In this case, we have this state converter actually moving or translating the polarization degree of freedom qubit into time bend qubit. Also, the vertical polarization here will be translated into horizontal polarization using this polarization controller on the shorter arm. So A will be changed to H. After that, going through the optical fiber channel to Alice and the Faraday mirror. This FM or Faraday mirror is not a traditional mirror. What is the difference between Faraday mirror and the mirror, the traditional mirror? Faraday mirror will reflect the photon. The photon will have orthogonal polarization, orthogonal to the input polarization. So in this case, we'll have, instead of horizontal polarization, we'll have a vertical polarization. We have still the time band, and Alice encoded the photon by a phase phi. Through the state converter, we will transfer back the time band state T long and T short to H and V, and the vertical polarization will be translated into B in this case. So all photons going from Bob to Alice will return back through the secure arm here and will be detected by the detectors in the secure path. What if Eve intercepts the photon? So the photon will go to Alice and return back to Eve. Eve will intercept the photon in case of attack and measure it and generate another photon with these mixed states, general state, going through the state converter. Sorry about this, something like compatibility issue between the Mac and the Windows here. But we have here a state for the photon after the polarizing beam splitter. Perhaps the second one will be good. Okay. So let's move to the PDF, will be better. Full screen. أنا فاكره. So here we have the state of the photon after reaching the polarizing beam splitter, and then we will trace over the polarization. We have this spatial state. As we see, there is a probability for each photon to be detected in the alert path. This is a problem for Eve because all photons generated by Eve cannot actually pass this test because there will be always a probability for the photon to be detected in the alert path, and we have actually calculated it in this form. So we have probability for Eve, we have BA, probability that photon will be detected in the alert path, and the BB, that the photon will be detected in the secure path. Okay, if we have number of photons like detector control attack, if we have number of photons, this probability will affect the energy of the photons detected on the alert path and the other energy in the secure path. We have EA and EB, the energy detected at alert and the alert path, and EB in the secure path. We relied on the click probability for one of the commercial products, detector products, single photon products for ID Quantique. This is one's experimental measurement here for the click probability versus the trigger pulse energy. We model or approximate this click probability by ramp step function to complete the calculations, and we could calculate the alert rate through this form and the shifted key rate. The alert rate is the rate that detector control attack will trigger photons on the alert, trigger detector on the alert path. And the shifted key rate is the rate that photons will be triggering the secure path detectors. Under some assumptions which are realistic, we could have the shifted key and the alert key here. In this figure, we have the shifted key rate after detector control attack in green, and the alert rate in red. As you see, for different values of blinding power, we have forever the alert rate is higher than the shifted key rate. So whenever Eve generate detector control or launch a detector control attack, the alert rate will be higher than the shifted key rate. Our lab, Quantum Communications and Cryptography lab, established in 2023. We have established quantum random number generator in this lab, FPGA-based coincidence measurement and quantum photonic simulator and single photon source. And under construction, we have the quantum key distribution system. This is a group of researchers. We have here Ahmed and the lab equipments. This quantum random number generator, we have established it in our lab. It's FPGA and connected by single photon detectors and connected via Ethernet to laptop. And we could generate random sequence, which is physically random at a rate about 28 megabit per second, physical random sequences. And we also constructed coincidence detection measurement based on the FPGA and the LabVIEW, and printable single photon source. We also worked on quantum photonic simulators. This is a version 1, and we have version 2, totally Python, and you can just line by line introduce something like you have phase shifter, beam splitter, and some input state, and you will have the unitary gate that describes this optical this optical setup and the probability of the photon to be measured on any of these passes. So the conclusion, despite quantum key distribution is unconditionally secure for ideal systems, but for some imperfections, we have vulnerabilities. We have introduced a quantum key distribution system that produces count rate on the alert detector for any state generated by Eve. These some applications related to our quantum key distribution system in GLT and in QCrypt and in Caleo, and we have a US patent in the last year. So.
Thanks, Dr. Salim, for the nice presentation and the great work. Please, does anyone have a question? Yes.
I have like there's something in the circuit just I wanted to ask about like 5-6 slides back if you can show it, please.
Okay. Which slide?
Towards the end. Yeah, more up. Again. Yes. Here you go. The loops in the circuit, like the one labeled PC and like what does these loops do?
PCI?
Like PC and like
Polarization controller?
what does the loops do? Like what are their
Okay.
functions?
Good question. Okay. So you are asking about the polarization controller. Its function is as written here. Polarization controller is just a rotator, polarization rotator. Okay, but it works on the optical fiber connections. Okay, so we have a polarization rotator, an optical fiber that transfer horizontal to vertical photons or vertical to horizontal. Okay, something like quantum not gate. Quantum not gate. It's just moving between 0 and 1, and if you have 0, you will have 1. If 1, 0. Alpha 0 plus beta 1, alpha 1 plus beta 0, and so on.
So for the time, then we are gonna stop here. We would like to thank Dr. Salim for the great presentation and this wonderful effort that has been highlighted. And feel free to ask him during the coffee break and the lunch. Thanks again, Dr. Salim. دلوقتي بنتحرك لدكتور محمد زيدان. Now we're heading to our next talk by Dr. محمد زيدان. We welcome Dr. Mohammed Zidan. Dr. Mohammed Zidan is an associate professor in the AI department at the Faculty of Computers and AI at Ghazal University, Egypt. He holds granted patent from the US Patent Office for his invention of the fastest ever main memory for quantum computers and has filed an additional 10 patents for innovations in quantum blockchain, quantum cryptography systems, and the quantum database systems. Dr. Zidan has published numerous papers in high-impact journals in the fields of quantum machine learning and quantum computing, and he serves as a reviewer for over 20 international journals and supervises more than 20 master's and PhD students, both in Egypt and globally. Okay, thanks.
Hello. Well, thank you, Dr. Taha, for having me in this interesting event. Today, I'm talking about inventions and advances in quantum computing. I'm trying to make some discussions as Arabic, not a discussion as English, but my research group is Professor منتصر قصيمة, Professor هشام نعيش, Professor محمود عبد العاطي. امبارح كان أحد الناس بتسأل في الجروب بتاعت الهاكاثون what about quantum engineering jobs. احنا مستقبلنا ايه في الكوانتم؟ انا كباحث لسه بادئ او كانجينير لسه بادئ, انا مستقبلي ايه؟ هاكل عيش في المجال ده ولا مش هاكل عيش؟ وكان رد بعض الناس كان محبط. اوكي, but the most interesting thing today we have the first quantum computing product in the Middle East. We developed the first quantum computing product in the Middle East. You can scan this QR code. Indeed, this graph generated by NVIDIA shows the required resources for the development of cutting-edge artificial intelligence systems. This graph explains a critical challenge. As large language models are training in ever-expanding sizes of datasets, the required resources in terms of the computing power and storage capacity of main memory increase exponentially. So, without a breakthrough, the development of cutting-edge for developing computing resources and memory technology, the advancement in quantum computing and artificial intelligence technology will be very slowly and costly. So, some researchers are motivated to develop what's called quantum machine learning. And there are many misconceptions and there are many mistakes in quantum machine learning. Why? والحقيقة إن بتجيني مسج كتير على الواتساب بتسألني إحنا إيه المشاكل عندنا في الكوانتم ماشين ليرنينج, كوانتم اي اي. بعض الريسيرشرز بيطبق التراديشنال اند كلاسيكال ماشين ليرنينج on quantum computing to optimize the topology of quantum circuits and then they publish their work as quantum AI. This is incorrect. This is not quantum AI. Here you have a classical machine learning وانت بتطبقه على quantum circuit. So the training process is performed for classical machine learning, not quantum machine learning. Okay? So this is not quantum machine. Okay? This is totally classical machine learning, not quantum machine learning. Okay? The second thing is that for variational quantum machine learning, there are many tricks. The researcher swamped in traps. ايه اللي بيحصل هنا؟ انت بيكون عندك الداتا سيت بتاعتك متخزنه اساسا في الكلاسيكال ماشين, في الكلاسيكال رام. سوري, انت عندك you have classical machine learning and stored in classical RAM. Then you encode the data from the RAM into qubits. Then you try. So here the reading process is classical complexity. This is what flow your work. The complexity here is classical complexity. So when you encode your data set into qubits, then you apply some and that, okay, or some variational circuits. Then you make measurements. Then you apply classical machine learning algorithm, what's called classical optimizer. So what is the advantage? No advantage. وللأسف ابحاث ابحاث كتير جدا منشوره في باسم ان احنا بنحقق الكوانتم ادفانتج. للاسف. وهوضح ايه السبب في نشر الابحاث دي. ليه الابحاث دي اتنشرت؟ طيب، لما نفحص الابحاث دي مش بنلاقي اي كوانتم ادفانتج من ناحيه التايم كومبلكسيتي ولا ميموري ادفانتج. بعض الباحثين بيدعوا ان هم عملوا ريديوسنج للبارامترز، ودي التريك. انت عملت ريديوسنج بارامترز، بس ايه الماشين اللي انت طبقت بيها؟ ايه الماشين اللي انت طبقت بيها؟ كلاسيكال. and you make classical simulation. فالريدكشن في النمبر اوف بارامترز حصل بسبب الماثماتيكال بروبرتيز بتاعت الهيربرت سبيس، ما حصلش بسبب الفيزيكال كوانتم. وبعد كده ما تقنعنيش انك انت هتجيب اكيورسي احسن من الكلاسيكال ديب ليرنينج. الكلاسيكال ديب ليرنينج دايما هتفرق. للاسف برضو بعض الابحاث بتتنشر على اساس ان الكلام ده كوانتم ماشين ليرنينج، وان هم بيحققوا الكوانتم ادفانتج. there is no quantum advantage. طيب، السؤال اللي بيطرح نفسه، ليه الابحاث دي بتتنشر؟ ليه الابحاث دي بتتنشر؟ لان الابحاث دي مش بتتبعت لمجلات متخصصه في الكوانتم كومبيوتنج، بتتبعت لمجلات متخصصه في الكمبيوتر ساينس. فالمحكمين ما بيكونوش متخصصين في الكوانتم، فالمحكم اول ما بيشوف حضرتك جبت اكيورسي اعلى من اي كلاسيكال ماشين ليرنينج موديل بيأكسبت البيبر. وفي ابحاث كتير جدا اتنشرت ان الكلام ده مش مظبوط. منهم بحث اتنشر في نيتشر تحت عنوان Variational Quantum Circuits are Swamped in Traps. اوكي. In 2021 we published a paper. In this paper we proved that quantum computers cannot only solve classical problems faster than classical computers, but can solve new types of problems that cannot be solved absolutely, even though these problems are quite simple using quantum computers. ومن هنا بنقدر بنعرف الماشين ليرنينج داتا سيتس الى نوعين. النوع الاول احنا بنسميه كلاسيكال ماشين ليرنينج داتا سيتس، وده اللي احنا ممكن نعلمها باستخدام يا اما الكلاسيكال ماشين ليرنينج او الهايبريد كوانتم ماشين ليرنينج او الاند تو اند كوانتم ماشين ليرنينج. في نوع جديد بقى اكوردنج للبيبر دي اسمه كوانتم داتا سيت. واتس كوانتم داتا سيت؟ Quantum dataset is a dataset that is produced from the sensors of quantum computers, what's called quantum sensing and quantum metrology applications. So you have quantum states that captured by quantum sensors. Can you save this dataset on HPC? Can you do this? Totally no. Totally no. Can you learn this using variational quantum sets? Totally no. You cannot do this. So we need type of quantum machine learning, what's called end-to-end quantum machine. Okay. But what is the roadmap to implement end-to-end quantum machine learning or hybrid quantum classical machine learning with quantum advantage in terms of time complexity? أول حاجة لابد من وجود quantum من memory، وتكون ليها تايم كومبلكسيتي اعلى من الكلاسيكال رام عشان نقدر نحقق الكوانتم ادفانتج. تاني نقطة، لازم يكون عندنا طريقة نعمل بيها ريكوجنيشن للنون اورثوجونال ستيتس عشان نقدر نعلم الهايبريد او الفاريشنال او الاند تو اند كوانتم ماشين ليرنينج في بولينوميال تايم. النقطة الثالثة ان احنا محتاجين، دي بقى النقطة احنا يا ريت كلنا نركز فيها، بدل ما نروح لابلكيشنز واحنا متاكدين ان احنا مش بنحقق كوانتم ادفانتج وندعي ان احنا بنقول احنا هنحقق فيها كوانتم ادفانتج، يا ريت نحل المشكله دي. احنا في الريسيرش بتاعنا حلينا اول مشكلتين. حلينا المشكله دي ان احنا اخترعنا اسرع كوانتم ميموري، وحلينا المشكله دي ان احنا قدرنا نبتكر طريقه نتعرف بيها على النون اورثوجونال ستيتس في البولينوميال تايم. حلنا المشكله دي. لو اتحلت المشكله الثالثه دي احنا هنقدر نحقق الاند تو اند كوانتم ماشين ليرنينج وذ كوانتم ادفانتج. دي النقطه اللي هي فيري تريكي. اوكي. ده نبذه عن الريسيرش ورك بتاعنا. وي ديفلوبد كوانتم artificial intelligence systems. We developed quantum algorithms that achieve quantum supremacy, and we invented some systems in quantum blockchains and quantum cryptocurrencies, and we invented some systems for quantum 3D printing, and we proved that quantum computing can solve new types of problems that cannot be solved absolutely using classical computers, and we published two papers on this topic. But to handle this challenge, we had to devise two key paradigms in quantum computing. The first thing is quantum in memory, and we developed a new quantum approach based on quantum entanglement to reduce the computing time from exponential, as seen in some problems with classical computers, to binomial time in quantum computing realm. So let me explain the second approach. Here, what is quantum state? What's quantum state? Is this entangled state? Is this entangled state? Is this entangled state? هل دي entangled state ولا لا؟ هل دي entangled state؟ لا. كويس. Stable probability. Good. طب دي. امم اوكي. entangled ولا لا؟ ماشي. طب دي entangled ولا لا؟ امم اوكي دي entangled. اوكي. ودي entangled or not? Huh? No. So, okay. This is entangled, okay? What about this? انتانجلد. اوكي جود. ودي انتانجلد، ايه رايكم؟ لا. طب هنشوف بعد شويه. طب what about this؟ مين اللي قال دي انتانجلد؟ انا بشكرك انك انت قلت لي. انا بشكرك انك انت قلت لي. للاسف النقطه دي بتبقى confusing لناس كتير جدا، وفي ناس بتمثلها بالاكزامبل بتاع الجلافز، بس this is not intended. في ناس بتقع في النقطه دي بتمثلها بفكره الجلافز اذا كان رايت او ليفت. اوكي this is not intended state. اوكي so absolutely this is separable state, not intended state. And what about this? Indeed, we have a measure for quantum entanglement. We have a measure for quantum entanglement. We have a formula that quantifies the degree of entanglement between any two qubits. This measure, there are many measures. The most effective one for two qubits is called concurrence. So concurrence, we can use this formula to quantify the degree of entanglement between any two qubits. Okay, so the concurrence may be between 0 and 1. So if you apply this formula on this state, it will be 0. Okay? Apply on this 0. Apply on this, not 0. Apply on this, not 0. So this and this are entangled state. Using this measure, we call this measure concurrence. It quantifies the degree of entanglement. How much entanglement between two qubit state. But can we apply this formula on quantum computer? We cannot apply this. This is a classical formula. So in 2020, we published a paper. For the first time, we say that the degree of entanglement can be used to solve interactable problems. If we can quantify the degree of entanglement between two qubits, then we can solve our problem. This is our model. We have some input state. This state may be prepared in a uniform superposition or received using quantum teleportation or quantum networking. Then we apply some computation. This computation may be machine learning, quantum machine learning, or maybe quantum computing, maybe any problem. Then we add ancilla qubit initialized in state 0. Then we apply an operator is called MZ. MZ create entanglement between these two qubits. Then we measure the degree of entanglement. After we measure the degree of entanglement between these two qubits, we can solve our problem. So you can use this model to develop your quantum machine learning algorithm, or you can develop your quantum AI algorithm or quantum computing algorithm, and you will achieve quantum. But there is a trick here. When you apply entanglement here, the entanglement may be actual entanglement or maybe virtual entanglement. What is the difference between actual entanglement and virtual entanglement? Actual entanglement means that these states cannot be factorized on all base states. This is the actual entanglement. So if we change the basis, we cannot factorize these two qubits. But there is a situation that these two qubits may be not factorizable in computational basis. So in computational basis, they are entangled. But when we apply some additional operator to make the entanglement between these two qubits is actually entangled, then we can make them actually entanglement. But if we calculate the concurrence before we apply the separator operator, or after applying the separator operator, the concurrence value will be the same. So we don't need to apply additional computation to make them actual entanglement. In this case, we call them virtual entanglement. Okay. Indeed, to solve your problems using this model, there are two theorems that says how can you solve your problem. Your problem always given by this formula or this formula, according which the probability of 4 zeros greater than 4 zeros or not. And if the other condition, then we change the solution here. There is another technique. There is another technique you can use to solve your problem, that if there is entanglement or not. This technique will be useful to solve some problems, and indeed the time complexity of this model is constant in a predefined area. So we provide this in 2 papers, and we proved that our model achieved quantum supremacy and faster than Groover. We published these papers for the first technique and these papers for the second technique. Also, using this technique, we invented some quantum blockchain systems and quantum cryptocurrency systems and filed these 2 patents. And in last week, we have granted this patent from US Patent Office for inventing the quantum consensus protocol for managing and mining quantum cryptocurrencies. What about main memory? اوكي انا عارف ان في ناس maybe physics maybe engineering maybe computer science، ولكن هتكلم شويه مع الناس اللي هم تخصصاتهم فيزيكس شويه، لان الكلام ده يعتبر بيزكس للكمبيوتر ساينس. احنا عارفين ان اي كلاسيكال بروسيسنج يونت، اي كومبيوتنج سيستم بيتكون من حاجتين: كلاسيكال كومبيوتنج يونت اند الكوانتم مين ميموري، سوري كلاسيكال مين ميموري which called the name random access memory. طيب what about the classical RAM? Classical RAM comprises a set of memory cells. Each memory cell is assigned an address. When a classical and RAM communicates classical processing units through 3 buses. The first bus is called classical data bus, and the second bus is called classical address bus, and the third one is called quantum control bus. When a classical processing unit needs to send or store data to a certain memory cell, it sends its address through the address bus and sends its data through the data bus and specifies the operation as write on the control bus. Subsequently, the data is written to this memory cell. On the other hand, when the classical processing unit needs to read a data from a certain memory cell, it sends its address through the address bus and specifies the operation as read on the control bus. Subsequently, the data is loaded to the classical processing unit through the data bus. What about the time complexity right to all memory cells in classical RAM? It is exponential. And the time complexity to read from all memory cells in classical RAM is exponential. Okay? And this makes your variational quantum machine learning is exponential. Okay? Because you read your data set from classical RAM. So any steps you do, it's the time complexity. Exponential. Okay? So when you have a classical AI algorithm that is executed by a classical processing unit, and we have a machine learning data set stored in RAM, then this algorithm is executed by a classical processing unit to train from the main memory. Many firms are striving diligently to develop what's called fault-tolerant quantum computer, and this graph explains their recent work. And recently, IBM announced that they have a clear roadmap to produce the first fault tolerant quantum computer by 2029. But what about quantum main memory? What about quantum main memory? All firms are working to develop the fault tolerant quantum computer. What about quantum main memory? Indeed, this motivated us to invent the fastest ever quantum main memory. We call our invented QRAM Q1 RAM. Why Q1? I will explain later. Our Q1 RAM communicates a quantum processing unit through 3 buses. The first bus is a quantum address bus, the second bus is a quantum data bus, and the third is quantum control bus. This is our invented quantum circuit, which has been granted the first patent by 2021 and the second patent by 2023 and the third one last week. The time complexity to write a classical data into our classical دي بقى النقطة المهمة. احنا كده بقى داخلين بقى ازاي الكوانتم ميموري بقى هتدي لك كوانتم ادفانتج. اوكي؟ لو انت عندك الداتا سيت بتاعتك الكلاسيكال داتا سيت خزنتها في الكلاسيكال رام. Our invented QRAM can write all this data at the same time on time complexity O1 and can read your data set at the same time with time complexity O1. And if you have a quantum dataset, quantum sensing dataset, our invented QRAM can write this dataset on time complexity O1 and can read it in time complexity O1. This is the fastest ever quantum main memory developed so far. Okay. وبالتالي لو انت عايز هنا بقى الكوانتم انتانجلمنت مش هيخلي البروس زي الكلاسيكال ماشين ليرنينج. انت في كلاسيكال ماشين ليرنينج مش عامل اي اعتبار للمين ميموري ولا عامل اي اعتبار للكوانتم بروسيسنج، لان في الكلاسيكال ماشين ليرنينج مفيش حاجه اسمها انتانجلمنت. هنا في الكوانتم بقى الكوانتم انتانجلمنت ده بيجبرنا ان احنا نعامل السيستم ككل واحنا بنديفلوب الكوانتم ماشين ليرنينج بتاعنا. فبالتالي مش هينفع انك تطور سكيلابل كوانتم ماشين ليرنينج بدون ما تاخد في حسبانك ازاي الكوانتم بروسيسور داخل، ازاي الكوانتم ميموري داخله، ازاي الداتا سيت بيحصل عليها تريننج. ده لازم ناخد في حسبان احنا بنطور الكوانتم ماشين ليرنينج الجوريزم. ليه؟ بسبب كوانتم انتانجلمنت. وبالتالي في الحاله دي احنا دلوقتي عندنا بقى كوانتم مين ميموري نقدر نربطها بالكوانتم بروسيسنج المتاح حاليا عشان نبدا نطور الكوانتم اي اي الجوريزم تقدر تاتشيف الكوانتم ادفانتج using physical quantum computer, not the mathematical properties of the Hilbert space using classical computer. By the way, when you achieve, I published in 2029 a paper that achieved machine learning advantage using the mathematical properties of Hilbert space. Okay, but we didn't call it quantum machine learning model. We called it inspired from مستوحى not quantum because we use the mathematical properties of the Hilbert space. Okay. By the way, دكتور سالم كان بيوضح على الكوانتم سايبر سكيورتي. طيب لو احنا دلوقتي عايزين بقى نطبق الكوانتم سايبر سكيورتي على اللارج سكيل، على السكيلبل ابلكيشن، عشان نطبق الكوانتم سايبر سكيورتي في الحاله دي احنا بيبقى عندنا المسج بتاعتنا هل هي سمول مسج ولا لارج سكيل مسج؟ لارج سكيل مسج هطبق عليها الكوانتم كي ديستريبيوشن. احنا بنعمل جنريشن بالكوانتم راندوم جنريتور فور اكزامبل ونعمل انكريبشن للمسج. اوكي، بالتالي هيبقى عندي المسج بتاعت كلاسيكال ولا كوانتم؟ كوانتم مسج. كوانتم مسج دي حجمها صغير ولا كبير؟ حجمها كبير، يبقى عايز ايه عشان تخزن فيه؟ كوانتم ميموري. تمام؟ يبقى لازم تخزن فين؟ في الكوانتم ميموري. هيحصل بافرنج ويحصل تليبورتيشن، او هنقل المسج بتاعتي بالكوانتم تليبورتيشن، هتروح الناحيه الثانيه، هستقبلها فين؟ هستقبلها فين؟ لازم يكون عندي كوانتم ميموري. لازم يكون عندي كوانتم ميموري عشان استقبل في المسج. اوكي؟ الدكتور احمد مهدي يمكن عنده كومنت. الداتا كلاسيكال هنحولها لكوانتم عشان اعرف اطبق عليها الكوانتم كي ديستريبيوشن، هحصل على كوانتم سوري كوانتم كي، كوانتم انكريبشن كي، كوانتم انكريبشن كي. Another technique, yeah, another technique. We have a message, and we developed this technique by the way. We have a message, we transfer our message into quantum state, so you have to encrypt it using quantum encryption key. This key will be developed by your algorithm or received by quantum key distribution or by any quantum way, and then you have a quantum key, a quantum encrypted message. هتخزنها فين؟ في كوانتم ميموري، لان هي لارج سكيل، عشان تنقلها الناحيه الثانيه. هنا بقى انت مجبر يكون عندك كوانتم ميموري تستقبل فيه مين؟ تستقبل فيه مين؟ المسج بتاعتك، عشان تقدر بعد كده تفكها ويتحول. يبقى اذا مش هتقدر تطور سكيلابل كوانتم سايبر سيكيورتي بدون الكوانتم ميموري. الكومنت بتاعتك وضحت يا احمد؟ اتفضل. Yeah. If you use register, how can you manage them? And this issue is announced by IBM. IBM developed what's called quantum-centric quantum computer. They perform some operation on Fukuoka supercomputer and another operation, another operations using quantum processing unit. Okay, but and they explain this problem. They have not a way that connect the calculation that was performed on the Fukuoka by the quantum computer. So they made this operation manually, and I will send the video that explains this problem. Our quantum RAM solves this problem to manage the operation that will be performed on Fukuoka, and then you try to apply on quantum computer. I will. Okay. So quantum registers can be used for small scale. You cannot use for large scale. So even though classical computers or our cellular phones, they are work based on RAM, not classical registers. Okay. What is the second comment?
Ahmed Qaddafi, I have a question about, is there any difference between the quantum memory or transmission and communication? Because in IBM,
This is a very good question.
yeah.
Yeah.
We don't
There is a difference, and we invented one for quantum communications, and this was the third one. This is we invented this quantum memory special for quantum communication, because there is a difference between the processing for quantum computing. Yeah.
But my second question is, do you see that we will reach Portugal or we will not?
When IBM produce the fourth generation quantum computer, our quantum memory will be ready for this.
Yeah, but we have our own plan. We know what.
Give me small seconds, and I will explain this. Okay. This is for quantum cybersecurity, also for quantum teleportation. What about if you need to teleport a bulk of qubits, not small individual qubits, not small qubits. What about if we have what about if we have a bulk of qubits? We need to teleport them. Also, quantum memory is desperately needed. Okay. By the way, American company from USA was communicated us to use our invented QRAM to develop their quantum bioinformatic system. في شركة في أمريكا لما عرفت إن إحنا عملنا الQRAM اتواصلوا معانا وطبقوه وبيحاولوا فعلا تتطبق عندهم في الكوانتم انفورماتيك سيستمز. This is IBM implementation. Dr. Ahmed, this is the IBM implementation. We implemented our invented QRAM. There is one invented by 2008 by Sisloid. Do you know Sisloid? He is a famous professor at MIT. Sisloid invented the first main memory. It's called bucket brigade. Okay, but he invented to work in qubits, not qubits. And some Canadian researchers transformed it to be implemented using qubits. And when IBM opened the quantum computer for us last year, we implemented our invented QRAM and compared with bucket brigade, which was invented by Sisloid, and our invented QRAM achieved a quantum supremacy by 751%. This is on IBM quantum computer. Also, we compared our invented QRAM with 16 gigabyte classical RAM. We implemented our QRAM using IBM quantum computer and compared with the time of 16 gigabyte, and this is the supremacy. We published some papers to use our QRAM to store data that is captured from the astronomy. And this table explains our invented QRAM. This is a very important table. This table explains our invented QRAM compared to all other QRAM architectures. If you see for the time complexity to access or memory cells, our invented QRAM is the fastest ever quantum memory. And for all other applications, for other functions that are related to writing data and reading data, some of these cannot be performed. But our do all operations. So our invented QRAM is the fastest ever quantum memory and the most efficient. دي برضو كانت يعني استوقفتني مقولة معالي وزير التعليم، بيقول أنا لو بقيت رقم 1 في تصنيفات البحث العلمي عالميا ومش عارفين نصنع إبرة ما يهمنيش. أنا مش هدفي كده، هدفنا الوصول للبحث العلمي يصنع ويطبق ويحل تحديات. And I agree. إيه فايدة إن أنا أطلع مليون بحث مش عارف أطبقهم في الواقع؟ ايه الفايده؟ ايه الفايده ان انا اعمل 10,000 بلد اختراع وانا مش عارف اطبق واحده فيهم في الواقع؟ So the research must be implemented. الحقيقه احنا عملنا ديسكشن مع IBM وهم مشكورين نصحونا ان احنا نعمل الستارت اب بتاعنا. الدكتور شيشه I think you know دكتور شيشه. He recommended us to build our startup for quantum memory. والحقيقه لما بدانا لقينا في دعم، يعني لقينا الدعم من الزملاء الدكاتره جوه مصر وبره مصر والباحثين دعمونا ان احنا نبني فعلا الستارت اب اللي تحول الكوانتم ميموري الى برودكت متاح النهارده نقدر نستخدمه النهارده. وفعلا طلعنا بيه ابحاث علميه، وفي شركه في امريكا بتحاول ان هي تعمل بيه كوانتم انفورماتكس. طيب ازاي حولنا الكيو رام هنا بقى؟ لما دخلنا للصناعه بقى لقينا في حاجات ميسنج، في حاجات ما كناش واخدين بالنا منها. تمام؟ زي حاجه بنسميها الكوانتم جيت واي في الريل تايم. لقينا المشكله دي ما اتحلتش ولا حد فكر فيها. ازاي يكون انا عندي داتا جايه من اي او تي سيستم في الريل تايم واخزنها عندي في الداتا سيت في السوبر بوزيشن؟ دي بروبلم ما حدش كان فكر فيها قبل. دي ما اكتشفناهاش غير احنا نحول كيو رام الى برودكت، وعملنا فيها اختراع في الكوانتم جيت واي. فبالتالي اصبح دلوقتي عندك كلاسيكال ماشين ليرنينج سيستم. اي نو ذا تايم. اوكي. So it can be provided to our quantum gateway, then can be develop your quantum machine learning using this hybrid system, and we develop the ecosystem, and this is the website. The website here have three options. You can try it for free for non-experts. لو انت مش عارف اي حاجه في الكوانتم كومبيوتنج، ده ديمو بيساعدك ازاي تعمل اي حاجه لو انت حتى مش عارف اي حاجه في الكوانتم كومبيوتنج. ده بقى للديفلوبرز والريسيرشرز والكوانتم كومبيوتنج. احنا بنوفر بلاتفورم تقدر تنتجريت الكوانتم ميموري بتاعنا في الالجوريزم بتاعك انت بتطوره، او في البرودكت بتاعك انت بتطوره. وتقدر تطبق على كوانتم كمبيوتر حقيقي او على سيميليتور. كمان بندي لك اي بي اي لو انت مش عايز تطور الالجوريزم بتاعك عندنا. الالجوريزم بتاعك مثلا سري، عايز تخليه عندك، احنا بنديك اي بي اي تقدر تطبق عندك على البلاتفورم بتاعتك، تقدر تنفذ سيمسلي يوزنج اي ريل كوانتم كمبيوتر او اي سيميليتور. وفي الاخر بندي لايسنس لاي شركه عايزه تصنع كوانتم كمبيوتر. برضه احنا لما طورنا الكيو رام هو fully compatible with Qiskit. الكيو 1 رام compatible totally with Qiskit. اوكي؟ بالتالي مش هتلاقي اي صعوبه انك انت تطور الالجوريزم بتاعك باستخدام الكيو رام. ده الكيو ار كود لو حد حابب يجرب السيستم. ثانك يو.
طبعا بنشكر يا دكتور محمد. Thanks very much Dr. Muhammad for this nice talk and also the impressive works and the presentation. اتفضل. احنا هناخد الاسئله. اتفضل.
شكرا، يعطيك العافيه.
هتكلم عن براحتنا ماشي عشان نوصل. حد عنده سؤال تاني؟
شغلوا مع الاي بي ام هاردوير يعني عندكم في الداتا سنتر في الانفرا بتاعتكم عندكم اي بي ام هاردوير شغالين بتكونكتوا بيه؟ طيب هي يعني الكيو رام دي سوبر كوندكتنج ولا هي عباره عن يعني انتوا ازاي بتكونكتوا مع الهاردوير؟
طبعا.
يعني قصدي هي ميد فور ايه؟ اوكي تمام، يعني هي معموله زي اي بي ام الكيو بي يو ان هو سوبر كوندكتنج وهكذا.
مع اي بلاتفورم سواء كان سوبر كوندكتور سواء كان كومبوننت سواء كان ناتشورال اتوم، هي مش بس مع كل
اوكي تمام.
اللي انت قلت ان انت هتشرحها
تايب كومبلكسيتي 1.
نطلع يا جماعه كوفي بريك 10 دقائق بالظبط ونرجع لو سمحت. 10 دقائق عشان الوقت عندنا فيري تايت، والا هنلغي الكوفي بريكس اللي في المستقبل. يلا 10 دقائق ونلاقيكم راجعين.
انا بالنسبه لي لما تماثيل الظروف بتتغير لا كتير فرق اصلا بص يا سلام عليك Exactly. يعني شيء عشان كده اللي هو مسوي لي اوبتمايزيشن بس خلينا يعني خلينا سوينا اصلاح انا في بس انا بقول لك السنه دي انا هاي واحده اللي سوينا اصلاح. طب انت السي على السي مش عارف ليش سوينا عربي. لا بس عارف شو سوينا السي لا في تقصير لانه احنا لا مش مسويين ماركتنج صح. مسويين ماركتنج صح. انا لما اشتغل على اساس في كثير شركات يعني Let's not هذا الشيء اللي هو مسوي الانتجريشن بين طب ماشي لو فرض ان جنسيتي لو طب بشكل ما مش موجوده في ازاي؟ ولا نجرب عندك
Yeah, I'll stay here.
والله سعيد انا اتفرجت مباريات طلعت كتير قعدنا نجري ورا الطلبه في الفنادق دلوقتي مش شغال اشتغل شوف بقى انور اخضر لا لا هو لا هينور اخضر بس نتكلم على هو يبدأ دلوقتي انا عارف دكتور نبدأ طب يا دكتور هو كده ألن لاين صح؟ تمام مش هو غالبا ربع ساعة ما اعرفش الموضوع يمشي ازاي الصراحه كل حاجه ستيشن مايك دي مش من هنا فوق
مش المايك ماشي المايك بس مش شغال خلي واحد بس شغال ليك مش يعني خلي واحد بس مفتوح بس علينا بقى مش في اللاين انا هدخل دلوقتي اشوف هو دخل في اللاين ولا لا
كمان طب ما كنا
هيدخل دلوقتي انا وبعد الدنيا نحاول نخلص كده بعض. ان شاء الله نحاول نخلص ثلاثة.
يا جماعة هيكون عندنا بس تعديل بسيط في الأجندة. هنبدأ مع ألان شانسي ريموتلي دلوقتي، وبعدين هيكون بعديها الدكتور شريف فريد، وبعدين هيكون بعد كده الأستاذة يسرى معانا، الباشمهندسة يسرى هتكون معانا بعد كده. ماشي، هناخد بقى توك الدكتورة يسرى وبعدين نشوف البي اي تور بعد كده.
وصل عندنا
هقول له دلوقتي. بيسمع المايك. أنا do you hear us?
Yes, I can hear you loud and clear.
Thanks.
Thank you.
Can you share your screen to test?
Sure. Let me share my screen.
And we have your slides also. We can share them from our own, but we wanted to test if you can share them.
Sure. Let me. So I'm sharing my screen.
Yes, it's visible now.
Yeah. So I've got.
We are going to introduce you first.
Thank you.
Okay, ladies and gentlemen, please have your seats. Just relax a few seats.
Now, let me introduce Alain Chancey. Alain Chancey is president of Mulcat SAS. Also, he is a member. There is echo. Yeah. He is a member of QEDC and Qualcy. Also, he is a founder of Quant Lane SASU and Alain Quant LLC. Also, is offering management consultant in and AI services. Now the talk for you, Alain.
Thank you, Asma. Thank you to the organizers. Thank you to all participants for having me remotely. Taha will help me present my slides It will be dense and short, 30 minutes, and hopefully I will be able to make a demo throughout this presentation. So
they can see your slides, Alain. So they can see your shared screen as well as your video.
Excellent. So let me share that this presentation, the opinions and statements are mine as President Molketsas. It's worth noting that I've been a Qiskit advocate since the end of 2021, so I have a bias in favor of IBM offering, especially IBM Quantum. And besides, I'm also, as you can see on this slide, a co-author of a book which came out in 2022, titled Quantum Chemistry and Computing for the Curious, illustrated with Python and Qiskit code. I'm an international speaker. I'm proud to share with you that I've been invited as a participant to the 2025 Quantum IBM Quantum Developer Conference in Atlanta in November this year. And I was also a participant in last year's event in Poughkeepsie. So for more details, please check my details on my LinkedIn profile, where you can reach me, by the way. Can also be reached, of course, on the Discord channel for Qiskit. Okay, so I will present an overview of the so-called sample-based quantum diagonalization, SQD for short, which is an algorithm which is very promising. And I will illustrate this promising algorithm with Jupyter notebooks, which I've published on GitHub. It's a public repo, and feel free to access it. Okay. This is the agenda. So first of all, I will put SQD in the context of the quantum-centric supercomputing, and then introduce what SQD is about, followed by two very interesting use cases, and finally, if time allows, a demo which reproduces one of the use case. Okay. Oops. So what is quantum-centric supercomputing? So it's a term coined by IBM, and this is the definition. Quantum-centric supercomputing is the future of high-performance computing and is the way to achieve near-term quantum advantage in chemistry, materials science, and other scientific applications. So this is extracted from a press release. IBM and Pascal initiate collaboration to define classical quantum integration for quantum-centric supercomputers, was back in June of last year. Technically, a quantum-centric supercomputer is comprised of, guess what, quantum processing units, graphical processing units, GPUs, which are now the component of high-performance computers, and CPUs. And we hold the view that this quantum-centric supercomputer is the key to unlock the next generation of computing. So I mean, it matters to view quantum computing as a key component of a wider offering, quantum-centric supercomputing. Okay. Now, what is sample-based quantum diagonalization? So I've extracted a definition which I think is easy to understand, and I quote: "Sample-based quantum diagonalization is a chemistry simulation technique." Well, that's what it was designed for at the beginning. Nowadays, we see opportunities of extending the application beyond chemistry. It uses the quantum computer to extract noisy distribution of possible electronic configuration of a molecule in the form of bit strings. So yeah, so basically the quantum computer is used as a sampler. Then the SQD runs a classical iterative correction, which is like it's actually an error mitigation technique, but a smart one, which basically leverages knowledge of the physical properties of the system, typically symmetries. Okay, and so there is hope and hints already that for large enough noisy quantum computer with low error rates, that this SQD algorithm has the potential to perform more efficiently than classical approximation methods. So it's worth mentioning that in the last couple of months and weeks, a number of papers have been published with variants of this SQD. And yeah, there are a number of posts. I would mention those by Jay Gambetta, for instance, on LinkedIn. Every week or so, there is a new paper coming out, a variant of SQD. So this is a very important algorithm. Oops. Yeah, so this is a zoom on the recovery loop, which is again error mitigation based on knowledge of the properties of the system. So it is illustrated on the right-hand side, and on the left-hand side there is the explanation. So first of all, on the left-hand side, on the right-hand side, the diagram shows a psi, which is a symbol which stands for a wave function. So we start with an ansatz. So it's a so-called LUCG ansatz. There is a definition, by the way, in the glossary, which is included in my presentation. So yeah, so the LUCG ansatz is at the moment a good compromise between the is to run a circuit, quantum circuit, and the challenge of having a very accurate a circuit which very accurately models the physical system. And so what's worth noting is that the unlike other methods that have been presented before, like the variational quantum eigensolver, VQE, the sampling is done only once. And the iteration, and there are iterations in the recovery loop, is done classically. So there is a big difference with the VQE algorithm because there is no gradient descent involving a quantum circuit. Okay. So the trick is to basically every quantum physics system, in particular those pertaining to Hamiltonians representing molecules chemistry, it boils down to solving a big algebraic linear algebra problem. Basically, it boils down to diagonalizing a big matrix. The issue is the matrix is so large that even the most powerful supercomputer, it cannot be achieved. So this method, based on sampling by a quantum circuit, the idea is that instead of having to or trying to diagonalize a huge matrix, instead it boils down to solving a number of smaller diagonalization matrices. So this is what is shown on the right, and this is, by the way, this was a topic in one of the labs of the quantum summer school. And so maybe some of the participants have already seen this in practice. So let's see the reason why this is the future as compared to, at least for chemistry applications. So in this, on the left-hand side, you see a table which summarizes the challenge for the iron-sulfur cluster simulation. On today's noisy quantum processing units, even the best ones, it's estimated it would take 3 million years to properly find the round state with the accuracy which is required to deliver value in the quantum chemistry arena. So definitely hopeless. Okay. With a much more promising and theoretically proven algorithm, the quantum phase estimation, on a fault-tolerant QPU, which we expect to have by the year in 2029, in a couple of years, it would still take 13 days running continuously on a fault-tolerant QPU. Well, that is beyond what is really practical because, it's in practice, unfortunately, even with the fault-tolerant QPU, it will be really challenging to run a calculation for such a long time. However, the very good news is that there has been experiments that have shown that SQD within a quantum-centric supercomputing framework, it only takes 2 hours to properly simulate the iron-sulfur cluster. At the bottom, I give the references. This is a very good result achieved by IBM, Cleveland Clinic, and RIKEN, who gave access to their Fugaku supercomputer, which is one of the most, if not the most powerful supercomputer available in the world. So this, in a nutshell, explains why it's worth nowadays focusing on SQD as compared to VQE or even QPE for quantum chemistry. Okay. The other very exciting use case, a collaboration by Lockheed Martin and IBM to conduct chemistry simulations to simulate the dissociation of the ground state triplet and first excited single states of methylene, which has the formula CH2. So their study is relevant for interstellar studies and also for combustion, for improving the performance of engines. So on the left-hand side, I've given credit for the images, but what's interesting about this methylene molecule is that it oscillates between 2 different states. And we'll look at that into details. There are 2 different configuration, the triplet and the single state. Okay. And it is important to properly model this behavior. Okay. So on this side, we see also that this study, which was made back in 2024, the researchers used the one of the best quantum device offered by IBM, and at the time it was 52 qubits. It's worth noting that during the quantum summer school and currently with the free plan, which is offered by IBM Quantum, anyone can access a much more powerful quantum device. Actually, 2 of them at the moment. I think there is a so-called IBM Brisbane, just a nickname for a quantum device, which has got 127 qubits, and IBM Torino, which has got 133 qubits. So bear in mind that when you add 1 qubit to a quantum device, in theory, at least you multiply the quantum volume by 2. So there is a huge difference between 52 qubits and 127 qubits. So it's amazing. It shows the speed at which there is progress in just about a year. Anyone, I will show you in my demo, can replicate an experiment with which is still cutting edge, but which much more powerful hardware. I think it's extraordinary. So in this slide, try and illustrate why, I mean, the gist of this experiment. So what the researchers achieved was to accurately capture the so-called first order phase transition between the singlet and triplet states of the methylene molecule. So on the synthesis diagram, so basically there is a between a carbon atom and a hydrogen atom, there is a bond, and it's the length of this bond can vary a bit, and what happens is when it changes, there is at some stage shown on this picture, there are several simulations. And for each one, you see the triplet and the singlet. At some stage, the two curves, but in the same simulation, they cross. They cross one another, and this is where the model predicts that there will be a first order phase transition. And so it matters to do that accurately. And the researchers claim that with the SQD within the quantum-centric supercomputing framework, that is not just the best quantum processing unit available, but also together with the powerful Fugaku, I think was Fugaku supercomputer. They not sure actually. Anyway, they managed to outperform or at least show results that do compete with the best classical simulation. Okay. So now it's demo time. So I will introduce the first demo. So it's to find an approximation to the not just the energy of the ground state, but also the configuration of the electrons for the so-called carbon single state. So on the right-hand side, you see the single state. The two electrons of the carbon are paired, and one orbital is empty. And there are two possible configurations. Whereas at the bottom of the diagram, on the right-hand side, you see the triplet. The two electrons are in different orbitals, and in the single state, the two electrons are paired with opposite spins, which results in a total spin of 0. Okay. Whereas in the triplet state, I will show you the triplet state. So hold on, I will show you the triplet state before I move to the demo. The carbon's outer shell, there are two unpaired electrons which have parallel spins. So it leads to a total spin of 1. However, now this is just when I make the demo, with PyCF, which is a popular tool by Sensor Python for simulating chemistry, with PyCF, the spin parameter pertains to the number of unpaired electrons. So in the demo, we'll see a spin of 2, whereas actually, strictly speaking, it's a spin of 1. Okay, so now I will go back to the demo. It's actually I will click there to show you that it's actually available on my public repo, SQD Alain. So this is the nice Gradio-based interface. I will try and demonstrate it now. So bear with me. So hold on. Yep. So I've prepared this. So this is a Jupyter notebook, and it's well documented. So basically, I will run it live. So I restart the kernel. Okay, and I run everything. Okay. So it just executes one Python script. Okay. It should do something very soon. Yes. Okay. So by the way, it uses the latest and greatest Qiskit version 2.1. So now I'm invited to open this And you see, this is the radio user interface. So I've got the name of the file where this experiment is saved. So I will load it. So it refreshes everything. So just to illustrate it, it's very easy for anyone who is interested to replicate the experiment. You just have to run the Jupyter Notebook, click on this button to load the configuration, and you see there where there is the formula CH2. If you want to run on an actual quantum processing unit, you just click there, and there you see it shows a drop-down list box with the IBM devices I'm allowed to use. And this is not hard-coded in the code, so that folks who have access to different sets of quantum devices would see whatever they are entitled to use. And in the future, if there is a new device, which will happen soon, you would see this drop-down list box updated. So none stands for list busy, and there is the okay. So this interface lets you actually run on actual quantum devices. And when everything is ready, and I could change some parameters, but they are already preset, I just save the configuration again, and it is running. If I look there, I can see a more detailed log of what's going on. And so it takes a while. This is not my most powerful laptop, by the way. So you see, it has done some computation. It's computed the classical energy classically. See the number of qubits, 26. It's beyond what can be simulated with the Air simulator on a laptop with I only have 32 gigabytes of memory available for Ubuntu. So what happens is this is achieved because there is a trick. Instead of attempting to simulate with Air simulator, which is a powerful simulator, the running of a quantum circuit, what we do is we use a nice function which generates 10,000 samples drawn from the uniform distribution, which is of course much worse than what we would expect from an actual sampling from a quantum circuit. But you will see, I mean, at least that's what the demo shows, that the recovery procedure is so efficient. Even if we start with the worst possible configuration, uniform distribution, at least then it works. And of course, this is the advantage of this work of mine, which is, by the way, based on it's. I give credit to the original author of the work from which my work is derived. But basically, with this interface, you can experiment comfortably, I would say, on your laptop. And then when you feel confident that this is running fine, then you can try and run it on a real quantum processing unit. So it takes a while. So while it is doing that, I will just show you the results what we have with the triplet. So with the triplet, it's the same. It's very similar, except that there is a spin. Again, it's the number of unpaired electrons, which is 2, but otherwise it's very similar. Same, of course, formula. And yeah, it takes the post-processing takes some effort, even on a fairly powerful laptop, and it does converge after, I would say, 160. So it's about 2 minutes and a half, I would say, and it does converge. So this was achieved on another laptop of mine. So the singlet we see it starts improving from one iteration to the other. What I would like to show you is an illustration of what has been done with nitrogen, which was, by the way, a use case for the quantum summer school. So using a bit string from a previous run, this is what we achieve. So in other words, that replicates what we would get by running on an actual quantum processing unit. And what I've done, so you see, after 9 iterations, this SQD, which is the level of accuracy, so-called chemical accuracy, which is 10 to the power minus 3, 1,000ths. But remember that this accuracy has been estimated. It's from a classical calculation. Okay, and if I start with a uniform distribution, so you see, it's worse. Eventually, after 12 iterations, starting from a uniform distribution, eventually it does convert. But you see, so that there are limits to what can be achieved with starting from a uniform distribution of bit strings, as opposed to starting with a better quality one, which is you would get from running on an actual quantum processing unit. Okay, so we can have a look, see what's going on there. So you see, it has done 2 iterations. Okay, so in the interest of time, I will go back to my presentation. And basically that's it. That's what I wanted to show. That the amazing progress which has been made in less than a year, and the ability to replicate a very promising experiment on a laptop, and with the opportunity to run it on a quantum processing unit, which you can access. The free plan provided by IBM Quantum lets you have up to 10 minutes of runtime on an actual QPU per month. Okay, so just to mention that those of you who are not necessarily experts in quantum chemistry, don't worry, there is a glossary of terms which explains the basics. And if you want to dig in more, there is an extensive bibliography of everything which is about SQD. So this concludes my presentation. I don't know how we are doing with time, but if there are any questions, I'm available. Okay.
Yeah, thanks, Alain, very much for the nice presentation and also the nice work representing everybody in it. Yeah. So people are clapping here at the presentation. I don't know if you can see the camera, but we have a question here.
Yes, please go ahead.
Yeah, thank you very much for a very interesting talk. Actually, for me, the SQD, the sample-based diagonalization or quantum diagonalization is very new to me, so I'm so interested. So actually, I'd like to know if you can kindly tell me, like, what's the difference here, or what's the advantage in comparison with the variational quantum eigenvalue solver, especially in the variational eigenvalue solver. Usually there is some constraints on the Hamiltonian that the approximation has to be polynomial, otherwise you won't get the speed up. So is this kind of constraint also there on the this sample quantum based diagonalization method?
So I would just show again these slides. I hope you can see it. Can you see it? Yes.
Yeah.
On the left-hand side, I think it summarizes well the challenge. VQE is still a promising approach, but unfortunately for quantum chemistry, and this is also well explained in the book which was published in 2022, it turns out that because there is a need to map fermionic Hamiltonian to a bosonic Hamiltonian, so there are different methods, but there is a cost for that. So And it turns out that the number of quantum circuits that must be executed it grows with the complexity of the system, i.e. the number of electrons, basically. And also the depth of the quantum circuits is huge. It's beyond reasonable, basically. So the number of gates with VQE, at least what has been documented so far, and refer to my book back in 2022, it's not reasonable because of the depth. And you see on the left-hand side, it turns out that the best experts have estimated 3 million years to simulate an iron sulfur cluster. Now, in my book, we only simulate fairly simple molecules like H2 and lithium hydrate. So, okay, it works, and you can successfully run it with Qiskit nature. Well, so it does work, but in practice, if we and this is the aim, this is the reason why there is so much work around quantum computing. If we want to outperform what can be achieved classically, even on the most powerful HPC system, then we have got to use another approach. And SQD and variants are much more promising. And by the way, there is a recent publication which shows that there is a hope also that SQD could be used not just for quantum chemistry. So the Hamiltonian, if basically the solution is within a subset of the whole Hilbert space. So I hope but again, I mean, look at the left-hand side. I mean, VQE for the iron sulfur cluster, 3 million years, whereas today, 2 hours on a within a quantum-centric supercomputing framework. So I hope it answers your question. Thank you for this question.
Thank you. Just so I mean, sorry, just quick follow up here. So can we get some bound on the complexity here, or is it difficult? I don't know.
It would be opening Pandora's box, but yeah, we can have a follow-on discussion. Say, for example, on one of the Discord channel for Qiskit, for example, and but yeah, I mean what we knew from back from 2022 basically is that for not so large molecules, in terms of complexity, it's exponential, basically. That's the problem. So the challenge we face classically, we have got a similar one in terms of the number of circuits and the number of measurements. So for each circuit, we need to make at least 1,000 measurements, and so because of this, the cost of mapping from fermionic to bosonic Hamiltonian, it boils down to and it is made even worse because well, the annoying thing about VQE is that the gradient descent is done classically. It's not done quantumly. So it turns out that issues have been found, well documented, barren plateaus and the like. So it's a combination of things. The quantum circuits, their depths much too large, completely unrealistic, and made even worse by the fact that the gradient descent sometimes fails. And because with the gradient descent, it's an NP-hard problem, by the way. And the gradient descent in VQE is done classically. So for all these reasons, it's hopeless to use VQE at least for the purpose of doing meaningful quantum chemistry simulations. A much more promising algorithm is quantum phase estimation, but it's maybe hopefully with the error-corrected quantum devices that IBM promises by 2029. Maybe we can make some interesting experiments. But still, on the left-hand side, you see for this iron sulfur cluster, 13 days, on a fault-tolerant QPU, 13 days, I think it's beyond what we should reasonably expect in terms of duration of. And if you interrupt the computation, of course, with QPE, you can have mid-circuit measurement and the like, but it means it would not be a pure QPE algorithm. It would be something that would try and work around the difficulty of having to run for such a long time. So that's all I can say. Please refer to the excellent video by I think it's Antonio Mezzacapo. Yeah, and it's in my bibliography. He explains very well why SQD is very promising. Okay.
Thank you. Just one comment. Can we get access to your book? Is it available? We can access or yeah.
Oh yeah, I mean the book is offered unpacked by Pack Publishing and also on Amazon, and even better, there is a unpacked GitHub repo. There is a set of so-called companion Jupyter notebooks, and so whoever purchases the book is entitled to download a set of so-called complete Jupyter notebooks, which basically an executable version of the book. The lead author is Dr. Kipalen Sharkey, and I'm the co-author. Basically, I'm the one who made the Qiskit and Python illustrations, and so there is a cut down version of the Jupyter notebooks, which is publicly available, and on my repo. You can check on my repo. You will find a. So I guess I can show you actually, because we share. So let's see. Yes, if I share, you should see. Okay, here you see. There is the quantum computing for the curious. Okay, so this is a fork of the original publication by Pack Publishing, but I've tried my best to maintain it so you can even run again the examples given in the book with this version, which is still work in progress, with the latest and greatest release of Qiskit. So.
And feel free to send us the link so we can forward it now to the attendees here. And we have another, just to have another question. Yeah, just please make it quick. Raise your voice so we can hear it, and then I'm gonna transmit it again.
So yeah, so I think I can share it maybe in a chat of the Zoom. Let's see. Not sure. I will stop sharing. And I will put it in the chat. Okay. Okay. Oops.
Hi, can you hear me?
Yes.
Okay. So you mentioned that instead of air simulated, you use this specific function that was more efficient in simulating your SQD. So can I know about this function or what?
Yes, so it's a function which is available out of the box. I think with it's so I didn't write it. It's available as part of the I think SQD add-on, and I suggest you check my Jupyter notebook and you will see the link there. Let me share on the chat the link to the yeah, I just share the so yes, it's a function which generates a set of samples, uniform distribution. So very
okay, thank you. So another quick question. Does SQD need like a specific version of laptops to run?
Well, in practice, yes, because and I've got laptops which have got so I'm running Ubuntu under Windows, and there is 32 gigabytes out of 64 which are dedicated to Ubuntu, and yes, for that kind of simulation, you are better off to have a fairly powerful laptop. Otherwise, it might take longer. It may not even run. You see, even the classical computation with this so-called 6-31G basis, refer to my glossary, it might fail. So even the classical part before we go to the actual SQD, the recovery loop, the classical evaluation estimation with PySCF might fail if you haven't got enough memory. So so the answer is yes, you need, I would say, ideally 32 gigabytes of RAM to be comfortable to run that.
Yeah, so just for the sake of time, we would like to thank Alain Chancey very much
Thank
for
you.
the nice work and nice discussion, nice presentation.
Thank you, Tara. Thank you all for having me. Thank
Yeah,
you.
thanks, Anna. We've been honored to have you in the hackathon here. And now we are moving to our next speaker, Dr. Hani Ali.
Dr. Hani, can you share your screen?
Yes, I'm trying to share the screen. Just a second. I would have to go out and go in again, log in again to give
Yeah.
access to sharing. So I'm sorry. I will log out and log in again.
Okay.
Sure, and please also open your camera when you make the restart of the session.
Yeah, okay.
Let's welcome Dr. Hani Ali. Dr. Hani Ali is the senior measurement engineer at Quantware. He holds PSC in electrical engineering from Suez Canal University, then MSc from in microelectronics from Paris. After that, now his experience is mainly related to quantum computing. His PhD title is service code superconducting quantum processors from calibration to logical performance. His talk today is about how to establishing the first quantum computing lab in Africa. Welcome, Dr. Hani.
Yeah, hello everyone. I'm so happy to be here. Do you see my pointer and do you see the slides? I'm trying to move
Yes,
the
we see it.
pointer, so do you see the pointer at least?
Yes, we see it.
Okay, perfect. So hello everyone. I'm so happy to be here today. I'm Hani Ali. Well, let's cut the introduction down. I did my PhD at TU Delft, where I focused on calibrating and characterizing superconducting devices. My focus was implementing a distance resurface code based on the surface code architecture and superconducting transmon qubits. Today, I'm excited to talk about establishing the first quantum computing and sensing lab in Egypt, I would say in Africa, because up to my knowledge, I don't think there is actually a quantum computing lab in the whole African continent. So I'm very excited about this. I think this gives hope to the younger generation to join the quantum race. Quantum is one of the promising technology, as I will show later, and we are in talks with some key profiles in Egypt and some key professors, which hopefully will help us establishing that lab and keeping the expertise of quantum in Egypt to grow and working on multiple area or multiple aspects of the quantum computer, as I will explain in my slides. So let's get started. So many people believe that the next technology, the next computer will be based on quantum. This is an opposite to classical computers, which information are encoded into zeros and ones, while in quantum, this is a computer that performs processing, encode information based on some quantum mechanics phenomena, such as quantum superposition and quantum entanglement. You probably heard of it in high school, and if you're a physics student, you probably heard of it in your undergrad study or your master study. So I won't dive deep into the meaning of these, but I will try to give an introduction to the general audience who may not know what is a quantum computer. So this is a fast comparison between classical and quantum computer. So the basic units of information are represented in zeros and ones in the classical computer. On the quantum computer, it's a bit different. It's normally like a sphere, and the information are encoded in zeros and ones, and combination between zeros and ones, what we call quantum superposition. This gives a lot of computational power for quantum, as you have so many states, but also gives a lot of degrees of freedom where noise can be introduced. I will come to this later. The basic unit of a classical computer is based on transistors, actually from the 50s and 60s, where people developed that. And now we see, even in your hand, you hold a computer, believe it or not, that your smartphone is actually a computer, a very good computer with respect to the ones that we were developing in the 80s and 70s. And now quantum computer is more or less like the 70s and 80s of the previous classical computer period. So we are still, like, quantum computers are very big in size. They are not optimized. They are still at the proof of principle experiments. There are many platforms for quantum computer, many physical platforms where this information is processed and encoded and so on. One of the very interesting ones, or one of the many famous platforms, is the superconducting qubits. They have different families. You probably heard of transmon, fluxonium, and other types of qubits. There are also other ones using ion traps, using photonics, using different types of physical platforms to have this quantum phenomena on a micro scale or in a macro scale. The error rate for classical computers, they are quite low, extremely low, actually, extremely rare. This is 10 to the power minus 18 at best. So this is like a it's very, very rare to get an error on classical computer. In quantum, as I explained here, since you have a sphere, you have a lot of degrees of freedom, especially the phase degree of freedom, where errors also can be introduced. So it's a lot more fragile. The best error rate so far, physically, I would say 10 to minus 4, or on average, it's actually 10 to minus 3. So it's very fragile. Like, it's likely every 1,000 computation, you get an error. So this is not a reliable computer, right? If anyone from computer science here would laugh at me if I say every 1,000 computation we have an error. This is like very, very fragile. So there are many techniques to improve that error rate, or actually to decrease that error rate, to perform as good as the classical computer. We are not yet at this stage. There are a lot of proof of principle experiments that try to improve that error rate. Or when I say improve, I mean decrease that error rate. The source of error on classical computers, they can be from the clock jitter or background radiation. But as I said, these are very rare events. In classical computer, on quantum computer, there are many sources of errors, such as temperature fluctuation, microwave background, and also environmental noise, electromagnetic noise, and so on. So it's a lot more, it couples a lot to the environment, and since it has a lot of degrees of freedom, you also introduce all these errors. So that's why it's a lot more fragile. That's why we need error correction, especially for the quantum case, because we know no matter what we do, an error will happen. So we better think, what if an error happens? And that's what you heard that's what you hear like an error correction term for. So since we know that an error will happen no matter what, so what we are trying to do is to detect when an error happens, and when an error happens, detect it and then therefore correct it, or even both select it out. So we would like to have an error detection and therefore error correction, where we can then improve our error rate. People imagine doing this, like imagine you have a key and you want to save this key. So you create so many copies of that key. And this is what we are trying to do here. We create so many copies of the state that we want to protect. And we call that, so the state that we want to protect is encoded in physical qubits. And what we want to create is something called logical qubit, where we create all these copies, and even if error happens throughout the computation, because of this redundancy in the system, you will be able to retrieve the good state. So this preserves your ability to process and encode the right information. Okay, here is one example for the classical versus quantum. As I said, the quantum is encoded on something like a sphere, where often people refer to the 0 state in the top and the 1 state at the bottom. Technically, any point on the surface of that sphere can represent a state. So you can imagine, you can actually already visually see that the computational power for quantum is much larger than the one for classical computer, because you have so many states you can encode here versus only 2 states there. But as I said, it's a lot more fragile. It introduces a lot of noise and so on. So this is essentially, without going too much details, this is essentially what gives quantum computer a benefit to run faster than classical computers for certain problems. So this is with something called quantum entanglement. I will not go through this, but just know the term, and also quantum interference. That gives the quantum computer a vast solution space. Like they can explore a lot of solution in space, because they have a lot of encoded states, they have a lot of computational power, so they can explore much complex problem much faster than the classical ones. So there is a certain class of problems where quantum computer outperform the classical one. So quantum computer will not be used in laptops and will not be widely used everywhere. That's not the point. Quantum computer will be like a laser and a lamp. So the lamp exists everywhere. We use it everywhere. We have a laser which is much more powerful than the lamp, but the laser is being used in certain applications. It's not replacing the lamp. So this analogy works also for quantum and classical. So the classical computer will stay. Actually, part of the quantum computer is a classical computer. As Alan was explaining, we do computation using classical computers. And actually, the better you have a classical computer, the better your calculation is. So part of your, what you call a quantum computer, is actually fairly classical. So it will not replace the classical computer, but it will be using it in certain applications. And there is a certain class of problems where it's really hard to solve by classical computers. And it is actually the problem when you have when the size of the problem grows exponentially. So for example, you have, I don't know, take any other any simple example, even like delivery. What is the optimal, if you have a delivery guy and you want to minimize the costs per restaurant, for example, you have a lot of roads until this delivery guy reaches a target and deliver the food, for example. Imagine like now we want to minimize that problem. We want to optimize the cost. We want to minimize the cost. So there are so many factors that you can take. Like, for example, the traffic, the roads, is it ready or not, the gasoline costs, and so on. So the problem, if you think about the variables in this simple example, you will see the problem, it grows exponentially. And this can go for anything, like any optimization problem that has so many variations. Classical computers fail to solve the problem if it grows exponentially hard. Because of the computational power, it grows exponentially, so like it takes years to solve. So these are the type of problems that quantum computer promised to solve. For example, a factorization problem. Factorization is a key backbone for encryption in banking systems and military communication. So if you have a large enough quantum computer, it grows actually with like this is a problem that grows exponentially with size. So if you have a large enough quantum computer, you will be able to break some encryption protocols that we currently use for banking systems and military applications. And actually, that's a red flag for all national security people. So that's why people at the national level and governments are really interested in this technology to see where it goes. They know and understand that now it's very noisy, very fragile, but they don't know where it goes in the future. That's why a lot of fund in quantum now comes from the government and comes from armies, and they want to see where this technology is going. Another class of problem where also it grows exponentially and you have so many variations, input variations exponentially, is actually the molecular geometry. As Alan was explaining, these are the type of problems that a quantum Hamiltonian can perfectly describe the chemistry, the physics inside the molecule and inside the atom, because quantum mechanics actually is the running framework, is the actual framework that the atom uses and not uses, but it can describe the atom and the interactions with molecules very well. So quantum can naturally simulate some physics that is running down at the molecular level, and an example was like Alan was showing an example, but there are much more like there are variations of these examples, and actually people can use that. Imagine if we can simulate the chemical interactions between molecules very well, we can very well simulate and develop medicines, for example, that takes years before the medicine is approved, because we need the trial, we need the bed trials, and we need to make sure the medicine doesn't have any side effects and so on, because we lack the tool to develop the medicine and simulate that very well on a classical computer, because of the size of the problem that goes that goes exponentially with size, so we cannot simulate it classically. So this is a certain class of problem that would be perfect for a quantum computer, as it naturally mimic the Hamiltonian of these chemical interactions. Another class of problem is the searching over data structure. This goes over everything that you can imagine. This is like an optimization problem that happens. Like if you have an optimizer, if you want to optimize certain things, you have an optimizer that has so many inputs and so many variations, and searching over data structure or whatever the problem is, there is some quantum benefit by running these algorithms on a quantum computer versus that of a classical one. Okay, and there are many others, of course. There is like since we talk about AI, and AI is a hot topic these days, actually quantum computers can benefit from AI and can actually benefit AI, as in they can be used, AI can be used to in some decoding techniques for error correction using quantum computers, and quantum computers can be used in data centers to power AI. So they can empower and power AI, which is an interesting topic on its own. So as you see, there are so many applications and dimensions of these where quantum computers can be used. Okay, this is a map of the world and the quantum activities around the world. I want to invite you to look carefully at this map. You see there is a lot of activities in the US, a few activities in South America, a lot of activities in Europe, a few activities in Asia, in Australia, but you see Africa as a continent has no data point. And looking at that, and coming from Egypt, and actually I know a lot of friends who did their PhDs in the domain, they are experts on the field, like in the fields, but they somehow, Africa as a continent is missing the whole quantum activities. And that actually motivated me to contact some professors in Egypt, and there is a lot of work at the theoretical side, in Alexandria and in Alamein, and there are other universities who are doing great work at the theory side, also using simulations and so on. But I am just missing this lab, like having a lab there, building the expertise there, trying to teach students how to perform experiments on a physical quantum hardware and not just using an IBM computer, because using an IBM one, you would be able to run algorithms, but there are a lot of areas of expertise that are missing. You don't acquire that by just running experiments on an IBM quantum computer, which is great. Like, it's a great tool, it's great, but it doesn't teach you the lower level of things, like how to understand how quantum computer works, how a hardware works, how to perform characterization, calibration, improve the gate fidelities, and so on. This is something that is missing across the whole continent. And I think we will be making a history if we succeed to get a quantum computing lab in Egypt, because literally that will be the first one. And the students will benefit from that. Imagine master programs where people will be able to perform the experiments, the very experiments that they are studying. And that's much more powerful than running experiments online, which is again very good, but it would be great to have such a lab in Egypt. Okay, what a quantum computer looks like. Here I'm talking about my area of expertise, which is based on superconducting quantum computers. So there are so many physical platforms, as I explained, but I will only cover the superconducting transmon quantum processors. So this is something called dilution refrigerator. This dilution refrigerator is like a fridge in your home, where this fridge can actually achieve a millikelvin all the way down here. So these are different plates, different thermal plates, where they can achieve different temperatures. So you have here the 50 Kelvin, you have the 4 Kelvin, the 1 Kelvin, and then you have the 10 millikelvin. Why do we need this fridge? Because our device works in a very specific energy bandwidth, and this energy bandwidth is often referred to as 6 gigahertz for superconducting qubits. And in 6 gigahertz, if the device works just at room temperature, you have a lot of thermal noise that you cannot isolate these degrees. You have a lot of noise that couples to your qubit, so you don't have a perfect quantum system. And in order to have a quantum and coherent control, you need to minimize the thermal level. So that's why we need such a fridge to cool down the device, so we minimize the thermal noise and isolate the quantum system such that we can use it for computation. There are so many details here on the wiring. There are superconducting wires here that go superconducting below the critical temperature, where there is no resistance, because you also need this coherent control with no resistance. Resistance is a way of losses, right? And you need to minimize these losses. So we use superconductivity to minimize these losses and to keep the device cold enough such that the energy levels are well isolated from the environment. At the bottom, this is the quantum device. The quantum device is packaged in a PCB. Here you see two superconducting devices with microwave cables. So these are the cables that we use all the way, like we connect the device to these cables, and these cables carry the signal all the way outside where there is the classical electronics. So the device looks like this. These are superconducting microwave components. You have components for readouts, often called as CBWs. You have components for control. These are the main qubits, the layout for the main qubits here. This is the actual hardware of the quantum device. So this gets fabricated in the clean room. This is a microscale. So the scale here is like, the whole scale here maybe is a few millimeter. You're talking about maybe 10 millimeter or so. So they are fairly big structure with, if anyone is from a clean room background here, like, or uses clean room before, he would know that these structures are quite big, but they are still small with respect to the Yeah, it's not centi or meters and so on. They are millimeters here. Okay, these are the control electronics. These carry the signal away from measurement and control all the way down to the device. So the signal is carried out from this, we call that EWG or signal generators that transmit the signal all the way down through these superconducting lines all the way to the device here and back. Like we send control signals and we measure back what we see. And then from the data analysis and so on, like there is someone who's sitting behind a computer, who's a physicist or a quantum engineer, who actually performs the experiments and does the coding and stuff in order to understand perform control experiments to understand about the device, to know what's the device Hamiltonian parameters, to know T1, qubit frequency, resonator frequency, and so on. And also to take actions later and like for next experiments and so on. Okay, this is a full stack quantum computer. So like what I roughly presented here, these I'm presenting it in different layers here in stack. So let's look at this part here. So at the bottom, there's a quantum processor, and then there is a cryogenic and interconnects that carry down the signal all the way from room temperature or from the electronics to the quantum processor. And then there is the classical electronics at room temperature. There is someone sitting behind a computer trying to code and calibrate and control the qubit. And then at the end, there is a quantum application that you want to run. Like this can be the quantum algorithm and so on. So when you submit a job to an IBM processor or any other processor around the world, so what it does, it translates this circuit and this application that you want to run all the way down to these layers. So in every other lab, there are all these layers, and that's what a quantum computer lab is. So you have to have all these layers. Of course, there are so many companies around the world. Here I mentioned the Dutch ecosystem. And interacted closely with these companies, which is actually a spin-off from our group. And here I mentioned the tasks and the challenges for each of these layers. It's not, there are so many details here. It's not very important for now, but just for you to know, a quantum computer is not just one area of expertise. This is an interdisciplinary area that goes from design, fabrication, electronics, cabling, people who know the quantum physics, people who design algorithms, people who do the analysis and so on. So it's like an interdisciplinary area where it requires a lot of area of expertise. So even if your background is not in quantum, you can still contribute to it and you can still be part of it. And that's my main message to the younger generation here. If you are a student in electrical engineering or communication, you can still contribute to quantum in that way. If you are from software background or computer science, you can still contribute to have or to be part of the quantum computing race. Okay, so let's focus on, let's take what is the technicality and what are the area of expertise that we need to have if we want to have such a lab in Egypt. You at the quantum processor level, you need someone who knows the design. This is electromagnetic simulation using COMSOL, using ANSYS, using your own software. It doesn't really matter. But someone who knows electromagnetism and who solves Maxwell equations and can extract the capacitive network of a certain geometry, the geometry-based electromagnetic simulations. There is also the micro and nano fabrication. Anyone who knows microfabrication or nanofabrication is highly appreciated in the quantum field because the device is fabricated using these tools that you would actually normally use for semiconductor industry. So there are actually few clean rooms in Egypt. There is one in the AOC, and there is one in Zweil. I remember there is another one in the national, one of the national labs. So there are people who can already contribute to fabricating a quantum device. Of course, the metrics are different in quantum, but the tools are similar. And then the next layer, you need someone who knows low temperature measurement, filtering, signal amplification, signal noise, signal integrity, like it's mainly signal processing. So anyone with a background in signal processing would actually contribute at this layer here. And then for the control electronics, you need someone who knows microwave engineering or analog circuit design or FPGAs. These are wide area of expertise. You cannot have all these areas of expertise, right? So like it's in quantum, when I talk about quantum computer, like there is like a few hundred of people that are around when we are talking about Google, IBM, and so on, they have all these area of expertise covering wide range. So they have 400 people they are technically experts in all these areas that cover all these areas. And then there is at the control side, there is like the software engineering background would be highly appreciated, writing software in Python or in other languages like C and C++, writing a modular software that would scale with a number of qubits. It's one of the interesting topics. Also performing data analysis, doing when you do the averaging, how you extract the f of t of the signal, like analyzing signal in different dimensions and so on, normalizing the signal. And Python is one of the famous languages here. So if you are a young student and you don't know what to do, the first thing I really recommend you to do is to take a Python course. This languages, like coding languages, is like normal languages in science. If you don't know how to speak, then it's very hard to be part of it. So I really recommend the younger generation to learn any coding languages. If you know Python, then go and learn C. If you know C, go and learn C++, go and learn Java, and so on. And then the top layer is actually the quantum, like you need to be a quantum physicist to understand this. So this is about quantum physics, quantum Hamiltonians, the actual details of certain qubits or certain circuits. This is like the top layer of a quantum computer. But even if we have this layer, if we don't have all other bottom layers, then we don't have a quantum computer. So that's a main message here. For younger generations, try to position yourself in one of these area of expertise. And you have wide range of expertise here. And if you like the topic, then you try to position yourself in one of them. Okay, this is roughly if we want to have a lab in Egypt, we want to have the quantum device, the fridge, control electronics, and control software. For device, there are different vendors. Here I'm proposing Quantware with a 5-qubit device. So you are talking about, like, if you know the literature, you will hear people talking about 100 qubit, or even some people talk about a few hundred of qubits up to 1,000 qubit. Here we are talking about 5 qubits, so it's not like a very complex device, but it's a very good device to start with. This is where you grow your area of expertise, where students can learn. It's simple enough so that you can learn already, because you see it's already difficult because of all these different backgrounds that you need to have to establish a lab. For the fridge, there is the very famous one is the Blue Force fridge. There are different type of fridges, but here I choose a fridge that is compatible with the 5-qubit device. And for the control electronics, there are so many FPGA-based control electronics on different companies. Here I'm proposing Qblocks. And then at the end, there is a control software, which this is the part that people and students can contribute to. They can write their own software, but you need the software to control there are different levels of software. There is a software that talks to the machine and controls the physical instruments. And there is a software that is an upper layer that actually performs data analysis. And there is a software that does and perform experiments. So there are different layers of software. Here I'm proposing for the drivers, we would use one that is compatible with the rest of these choices. And students will contribute to that software at this point. And then here I'm mentioning the financial details of these devices. So overall, I don't want to go over the financial technical details here, but roughly it's about 700K in euro. or yeah, it's up to 1 million, honestly. Like if you count all the other things that you would need, you need an area where there is water cooling, there is an oil pipe, and there is a water cooling pipe, and there is and there is a good enough area to host all these components. And of course you need the technical expertise. You need students to, well, you first need someone who knows the thing, and then after you need students to learn, and then the first generation would teach the second generation, and it goes forward. So this is like an open architecture. You can choose to do that with one company like IBM or IQM, or I don't think Google does this, but there is another like you can choose to ask one company to do all that for you. And of course, this is more expensive than doing it yourself, like establishing and ordering it from different companies, and it's about 1 million in euro. So the question to you now is 1 million, can't we afford to have 1 million to spend on a very promising technology to build an area of expertise here? I think the answer should be yes. This is not, maybe this is inexpensive for an individual person, but if you are talking about a country or a continent, Africa is much more rich than 1 million. It should be. And there should be a lab in Africa and in Egypt, honestly, because we have the technical quality. It's not that we don't have the technical quality. We have people who already studied this, and they know that, and they are part of these bigger companies that you are buying the device from. So we should aim to have one lab in Egypt, at least one. Okay, this setup capability can host the 5 flux tunable transmons. This in parallel, you can also measure resonators using something called vector network analyzer. So this can be used for not just for quantum computation, but also for quantum sensing. Students can learn and do experiments themselves. They can learn how to characterize and calibrate a quantum device. They can build their own software on top in order to in order to perform experiments, do the different data analysis, publishing papers, doing research. And then plus, if we have a clean room, we can even characterize our own device. Or if we have people who their area of expertise are in FPGAs and control electronics, we can even have our own and control like our own control electronics and our own companies. As you see around the world, there are many startups who are starting at different layers of the stack. There are companies who are specialized in control electronics software, calibration software for quantum, and so on. There are many companies around the world, many startups. And the hope is when you have such an activity in Egypt, you will keep the technical expertise in Egypt. You will grow that expertise over time, and you will have different startups over time. So what you think about this 1 million is not actually, this is an investment, a large investment for a whole country. This is not just 1 million that you spend now and it's kind of lost. The potential of this is millions. If you see the funding raised for different companies now for Series A and Series B funding, you see the evaluation for these companies, startups that started a few years ago, like 3-4 years ago. The evaluation for the company is 300 million and 500 million for different companies, of course. So the potential here is huge. It's not just doing research for fun, but this is growing the area of expertise in-house. At the end, I want to share 2 exciting news. So this lab will not be visible without someone who knows how to do experiments. And I have some connections with some people in the quantum domain. So I got to talk to a few people, and there are 2 exciting positions that they could hire for. It's actually the TII in Abu Dhabi. So this is, as I'm working as a consultant there. So I got to know there are 2 positions. So this is the 2 positions. If you know the theoretical framework of superconducting qubits, you know the basic knowledge of how to control and measure a qubit. You don't have to have an experimental experience because, again, there is no experimental lab in Egypt. But if you know that and you know Python, you know Git or GitLab, and you know version control for coding and so on, you know, like a little bit of software background, basic data analysis, then this first position is great for you. So you will be learning how to measure a superconducting device on an actual quantum computer. So you will see and deal with all these layers. You will be writing code and understanding the output of a quantum device. The other position is on the design part. So if anyone who knows the theoretical knowledge of superconducting transmon Hamiltonian, James Cumming Hamiltonian, qubit-qubit interaction Hamiltonian, or know COMSOL multiphysics, ANSYS, perform electromagnetic simulations, yeah, this will be great. This is another position for you. So TII will be covering all the associated costs, including the flight tickets, the visa-free fees, and salary that cover the living expenses in Abu Dhabi. And the duration of that position is from 6 to 9 months. It can be extended and negotiated. It's at least 6 months. So if you have less than that, then maybe that's not the position for you. If you have at least 6 months to do an internship in Abu Dhabi to learn from a quantum computing lab how to do these experiments, and then ideally these persons and individuals will go back and do the same with the establishing lab in Egypt. So this is a way to kind of create the expertise if we don't have it, like to take the experimental experience if you have it. So if any of you was interested and have a relevant profile, please reach out to me on this email. Only for the relevant profiles I will reply. I'm sorry I don't have too much time to reply to all emails, but I will reply only to the relevant profiles. So if you receive a reply, so you are selected for a higher level interview and so on. So thank you for your attention, and happy to receive any questions. Thank you.
Thank you very much, Dr. Hani. And Dr. Hani was kindly shared this position. So I asked him if he can share it with all of you. So if you have the right profile, please feel free to contact him. Unfortunately, we don't have much time for questions. However, on the group, if you have questions or anything, I will forward them to Dr. Hani. So thanks very much again, Dr. Hani, for the nice talk, and also this high level of like understanding the architecture of how to build a quantum computing lab and so on. So thanks very much. And so now I heard that this hall will be closed. I don't know about the time, but I would like to thank our guest again, Dr. Hani, and see you later. Yeah.
Yeah, thank you. Thank you. Bye.
يوسف البروجرام هتقول ايه؟
We have now 3 more talks. We are going to start them with, we have from Dr. Sharif and Dr. Yosra, and also from engineer Sameh Zaghloul. And then we have a short tour now.
Thank you, Dr. Shah. It's now time for the tour. So I think we'll have to catch it outside this hall. And then after lunch, we can resume the talks. Would that be okay?
Yes.
Okay.
So after lunch, we are gonna resume the talks.